In the vastness of the universe, a silent drama is unfolding. The Andromeda Galaxy, our cosmic neighbor, holds the secrets and celestial catastrophes that shaped its fate. Andromeda is not a simple spiral galaxy, but a colossal formation that spans more than 220,000 light-years and contains 1 trillion stars. But beneath its serene beauty lies a history marked by violent collisions and dramatic transformations. Astronomers have discovered that Andromeda's double core, a unique structural anomaly, hints at ancient galactic cannibalism when smaller galaxies were devoured to fuel its growth. At the heart of this giant, a supermassive black hole quietly consumes material, affecting the fate of everything around it. Join us today as we journey through Andromeda's hidden catastrophes. We'll explore its turbulent past together. We'll also look into its future, where a cosmic event will occur that will change the very fabric of the universe, forever transforming our world. At the end of the 19th century, the Andromeda Galaxy was cloaked in mystery. The first astronomers looking through their telescopes saw it as a fuzzy patch of light in the night sky. Many thought it was a nebula inside our Milky Way. The first major leap in understanding came with the advent of more powerful telescopes. In 1885, astronomers at Lick Observatory in California made a startling discovery. They observed a bright new star near the nucleus of the Andromeda Galaxy, which they named S Andromeda, or supernova SN 1885A. It was an extraordinary event. It was the first time a supernova had been observed outside the Milky Way. The sudden brightness was a beacon that broke through the misconceptions of the age. Initially, however, confusion arose. Could this be a nova, a typical phenomena within our galaxy? Or were we talking about something more substantial? The light curve of SN 1885A revealed its true nature. Unlike novae, which fade relatively quickly, the brightness of this supernova persisted for months. This indicated a cataclysmic explosion, a hallmark signaling the death of a massive star. Through careful analysis and advanced modeling, scientists have reconstructed the event. They believe that SN 1885 was a Type 1A supernova, a thermonuclear explosion of a white dwarf star in a binary system. The explosion was so powerful that it temporarily eclipsed the entire Andromeda Galaxy. The observations of SN 1885A had profound implications. It was a turning point in astronomy, setting the stage for the assumption that other galaxies exist and are composed of the same stellar phenomena as our own. The discovery paved the way for Edwin Hubble's subsequent work, which confirmed that Andromeda was indeed a separate galaxy and not part of the Milky Way. Today, however, thanks to a discovery made more than a century ago, we understand supernovae as crucial elements in the life cycle of stars, spread heavy elements throughout the universe, and have a broad understanding of the dynamic nature of galaxies. So Andromeda, stretching 260,000 light-years across, is home to a variety of celestial phenomena, especially in its central region and spiral arms. The central region of the galaxy is a busy hub of activity. It's home to a large concentration of stars, gas, and dust. At its center is a supermassive black hole, but the region is also characterized by a prominent double nucleus, an unusual feature that distinguishes Andromeda from many other galaxies, but more on that later. One of the most exciting aspects of Andromeda's central region is the ongoing star formation. Despite the presence of a supermassive black hole, Andromeda's core is a cradle of new stars. Areas of dense molecular clouds collapse under gravity, igniting nuclear fusion and giving rise to new stars. These stellar nurseries are very important for understanding the life cycle of stars and the evolution of galaxies. Andromeda's spiral arms are impressively complex. These arms are sites of intense star formation, where massive young stars illuminate the surrounding gas clouds, creating regions known as hydrogen-2 regions. These regions are ionized by the ultraviolet radiation from the hot young stars, causing them to glow brightly. However, spiral arms are not static. They are dynamic structures influenced by gravitational interactions and the galaxy's rotational forces. As gas and dust move through the arms, they encounter shock waves that compress the material, triggering further star formation. This cyclical process keeps the arms alive and full of young stars. However, in the vast expanse of Andromeda, some stars play a crucial role in our understanding of the cosmos. Prominent among them are variable stars, which change their brightness and provide insight into stellar processes and cosmic distances. In 1923, Edwin Hubble, using the 100-inch Hooker telescope at Mount Wilson Observatory, observed a star in Andromeda that forever changed our view of the universe. This star, later named M31V1, variously known as a Cepheid or Cepheid variable star. Variable Cepheids play a key role in astronomy because their predictable changes in brightness make them reliable standard candles for measuring cosmic distances. Before Hubble's discovery, the nature of spiral nebulae like Andromeda was hotly debated. In 1920, Harlow Shapley and Heber Curtis debated whether these nebulae were part of our Milky Way or separate galaxies. The dispute remained unresolved until Hubble identified M31V1 as a variable Cepheid in 1923. Henrietta Swan Leavitt's discovery of the period luminosity relationship played an important role in Hubble's work. The relationship shows that the greater the period of brightness variation of a Cepheid, the greater its intrinsic luminosity. By measuring the period and apparent magnitude of M31V1, Hubble was able to calculate its absolute magnitude and, therefore, the distance to Andromeda. Using the formula, Hubble determined that M31V1 was nearly 1,000,000 light-years away, well beyond the Milky Way. This groundbreaking discovery confirmed that Andromeda is a separate galaxy, greatly expanding the known universe. Today, amateur and professional astronomers alike continue to observe M31V1 and other variable stars with modern equipment. Modern CCD cameras, more sensitive than the photographic plates that Hubble used, allow even amateur astronomers to replicate Hubble's work. Cepheid variables such as M31V1 remain vital tools in cosmology to this day. They help astronomers measure distances to distant galaxies, calibrate other distance measurement methods, and refine our understanding of the scale and expansion of the universe. In addition to the Cepheids, there are other variable stars in Andromeda's spiral arms, including the RR Lyrae stars. These stars also serve as standard candles. Although they're less bright than the Cepheids, their study provides additional clues to the structure and mysterious history of Andromeda. And now for something equally interesting. Our nearest galactic neighbor keeps secrets that have puzzled astronomers for several decades. Among its many mysteries, two stand out: the presence of a double nucleus and the behavior of the central supermassive black hole. Detected by high-resolution imaging, Andromeda's nucleus represents a unique mystery. Unlike most galaxies that have a single central core, Andromeda exhibits two bright nuclei. This unusual structure has led scientists to propose various theories. One of the leading hypotheses suggests that the double nucleus is the result of a merger between a smaller galaxy and Andromeda. When the core of the smaller galaxy curls inward, two bright centers appear. The Hubble Space Telescope provided the first detailed images of this double nucleus, showing a dense cluster of stars around each nucleus. Subsequent observations by the Chandra X-ray Observatory and Very Large Telescope expanded our understanding, showing that one of the nuclei is likely the original nucleus of Andromeda and the other a remnant of a captured galaxy. At the very center of the galaxy is a supermassive black hole millions of times the mass of our Sun. Recent research using data from NASA's Spitzer Space Telescope has shed light on the eating habits of this colossal entity. Unlike the chaotic food consumption observed in other galaxies, the Andromeda black hole eats calmly. Streams of dust and gas, stretching thousands of light years away, feed it continuously. These spiraling dust streams, similar to water drainage, maintain a continuous but gentle flow of material into the black hole. Computer models suggest this constant flow prevents the large luminosity fluctuations, normally characteristic of black holes that absorb matter in the form of clumps. Instead, the matter forms a small disk of hot gas that gradually falls into the black hole, keeping it relatively calm. Ongoing research combining data from multiple telescopes and advanced simulations continues to unravel the unique structural features and enigmatic behavior of the nucleus, revealing the complex and fascinating nature of our neighboring galaxy. Among other things, however, Andromeda has a rich and dramatic history that has shaped its current structure. Recent studies show that the formation of Andromeda was marked by significant events. First, a massive burst of star formation laid the foundation for the galaxy. This was followed by a second wave of star formation caused by a large-scale wet merger, the collision of two gas-rich galaxies. Galactic archaeology has helped scientists in this endeavor. It involves studying old stars to understand the history of the galaxy. By analyzing the chemical composition and motion of these stars, scientists can reconstruct the past events that shaped the galaxy. Specifically in the case of Andromeda, the presence of old stars with different chemical compositions provides clues about its turbulent past. Andromeda experienced two distinct epochs of star formation. The first epoch was caused by a rapid accumulation of gas, resulting in a thick disk of stars. The second epoch, which occurred between 2 and 4.5 billion years ago, was most likely caused by a wet merger, resulting in a thinner and younger disk of stars. Over billions of years, Andromeda has grown to swallow more than 100 satellite galaxies. This process, known as galactic cannibalism, has significantly affected its structure and star formation. Such interactions not only increased its mass, but also triggered new waves of star formation. One of the most dramatic events in the history of Andromeda was the collision with the compact elliptical galaxy M32. This collision profoundly affected the spiral arms and overall structure of Andromeda. The gravitational interaction caused by M32 created ripples and warps in its disk. The collision with M32 caused significant perturbations in Andromeda's spiral arms, leading to their current structure. These interactions likely caused bursts of star formation, creating the bright young stars observed in the spiral arms even today. Andromeda is surrounded by numerous satellite galaxies, each of which plays a role in its evolution. In addition to M32, the second most important companion is NGC 205. Interactions with them have left notable traces on Andromeda, including gravitational warps and tidal streams. However, Andromeda's story is still unfolding. It's on a collision course with something less abstract and more dear to us. This future collision will lead to the formation of a new galaxy, radically changing our past forever. In about 4.5 billion years, a tremendous cosmic event will occur. The Andromeda Galaxy and the Milky Way will collide. This impending merger will forever change the structure of both galaxies, resulting in the formation of a new elliptical galaxy. The Andromeda Galaxy is currently moving toward the Milky Way at about 68 miles per second. This head-on collision is a rare event that's affected by the gravitational attraction between two massive bodies. Even though the distances are vast, the galaxies are destined to merge. The collision of the Milky Way and Andromeda will not be a sudden impact. but a very long process lasting several billion years. First, the galaxies will pass through each other, their gravitational forces creating tidal distortions. As a result of this interaction, stars and gas will escape from both galaxies, forming long tidal tails. After the first pass, the galaxies will continue to interact, eventually becoming a single, more stable structure. The process will lead to the formation of a new elliptical galaxy, which scientists have already given the name Milkomeda or Milkdromeda. The merger will cause the spiral arms to dissipate, transforming the galaxies into a more homogeneous, ellipsoidal shape. Although the merger will radically change the structure of galaxies, the vast distances between stars mean that direct collisions are unlikely. However, the solar system will be affected by the new gravitational forces. It may be thrown to another region of the new galaxy, or even ejected into intergalactic space. By the time of the merger, the Sun would have become a red giant, making Earth uninhabitable long before that. The Sun's increasing luminosity will cause radical changes on our planet, probably depriving it of its atmosphere and oceans. Therefore, with very few remains of humanity or any other life remaining on Earth, the direct impact of the collision will be very minimal. Impending changes are prompting us to consider the future of humankind. As our understanding of cosmic events grows, so does our ability to adapt and explore. The merger of Andromeda and the Milky Way may inspire future generations to find new homes among the stars, advancing our journey into space. And this always leads to thoughts about our place in space and the future of human civilization. How will we adapt to such changes? What steps can we take to ensure our survival and further exploration of the universe? As we continue to gaze at the stars, we're reminded of the incredible forces shaping our galaxy and the limitless possibilities that lie ahead. Imagine a colossal object 6 miles wide, hurtling through space at 12 miles per second toward Earth. And it's not science fiction. 66 million years ago, such an asteroid slammed into what's now the Yucatan Peninsula, forming the crater Chicxulub and triggering a mass extinction event. Today, our planet continues to be threatened by near-Earth objects. These include asteroids and comets, whose orbits bring them into our space neighborhood. NASA and other space agencies have made significant strides in tracking and understanding these potential threats, but the risk remains. Advanced technology is at work to monitor and mitigate these threats. From kinetic strikes to gravity tractors, humanity is developing strategies to protect our world from these stellar invaders. But what would happen if another Chicxulub-sized asteroid was on a collision course with Earth today? How prepared are we for such a catastrophic event? Join us to learn planetary defense, the history, science, and the future against such impressive threats. So 66 million years ago, an event occurred on Earth that was so catastrophic that it changed the course of life on the planet. The asteroid, about 6 miles in diameter, slammed into the Yucatan Peninsula in present-day Mexico, forming what we now call the Chicxulub crater. The immediate aftermath was nothing short of apocalyptic. The collision released energy equivalent to billions of nuclear bombs, caused forest fires and tsunamis, and threw huge amounts of debris into the atmosphere. The impact's most significant and long-lasting effect was the release of dust, soot, and sulfur aerosols into the atmosphere. These particles created a global cloud that blocked sunlight for an extended period, a phenomenon often referred to as impact winter. New research has shed light on the critical role of fine dust particles in this cataclysmic event. A study published in Nature Geoscience in October 2023 found that fine dust, particularly particles between 0.8 and 8 micrometers in diameter, played a significant role in abrupt climate change. The researchers collected 66 million-year-old rock samples from North Dakota, located an impressive distance from the impact site, which contained surprising amounts of these fine dust particles. These particles lingered in the atmosphere, forming a dense cloud that persisted for up to 20 years, with the first 5 to 8 years being the most severe. This long period of darkness led to a significant drop in global temperature, estimated at more than 18 degrees Fahrenheit, 10 degrees Celsius in the first year alone. As sunlight was blocked, photosynthesis stopped. Plants unable to produce food began to die out. This collapse of plant life had a cascading effect on the entire food chain. Herbivorous dinosaurs that relied on plants for their food, faced starvation. Consequently, the carnivorous dinosaurs that preyed on them also died. This chain reaction led to the extinction of about 75% of all species on Earth. Interestingly, the new study highlights the hitherto unnoticed impact of dust compared to soot and sulfur, which were previously thought to be the main culprits for the prolonged cooling period. The findings suggest that while soot and sulfur blocked sunlight more effectively, the sheer amount and persistence of dust had a profound and lasting impact. The study also provides insight into how some species managed to survive this dark period. Hibernating plants and animals had adaptations that allowed them to survive the prolonged lack of sunlight. However, the study casts doubt on the survival mechanisms of freshwater organisms, indicating that more research is needed to fully understand the specific mechanisms of death following a Chicxulub strike. So what are near-Earth objects? NEOs are asteroids, comets, and other celestial bodies whose orbits bring them close to Earth. These objects vary in size, from small, harmless rocks to massive bodies capable of causing a massive catastrophe. Asteroids are the rocky remnants of the early solar system, mostly found in the asteroid belt between Mars and Jupiter. Comets, on the other hand, originate from the outer regions of the solar system and are composed of ice, dust, and rocky material. As they approach the Sun, they develop luminous comas and tails. The danger posed by these objects depends on their size and trajectory. Although most NEOs are too small to cause significant damage, some, such as the Chicxulub impactor, are capable of causing global catastrophes. To mitigate these risks, space agencies such as NASA and the European Space Agency have developed extensive programs to track and detect NEOs. Telescopes around the world are constantly scanning the sky, and cataloging objects that are approaching Earth's orbit. One of the key instruments in this work is the Wide Field Infrared Survey Explorer, which has been repurposed for the NEOWISE mission. Hundreds of near-Earth asteroids have been discovered and characterized using this space telescope. The role of artificial intelligence in detecting unobserved asteroids is becoming increasingly important. In May 2024, an AI-based algorithm known as Trackless Heliocentric Orbit Recovery, or THOR for short, detected more than 27,000 previously unobserved asteroids in archival telescope images. This artificial intelligence tool analyzes huge amounts of data, identifying and tracking objects with remarkable efficiency. It can process up to 1.7 billion points of light in a single telescope image, connecting them into asteroid trajectories. The Vera C. Rubin Observatory, due to begin operations next year, will further enhance our ability to detect NEOs. Equipped with advanced artificial intelligence software such as HelioLink 3D, this observatory is expected to catalog millions of asteroids in its first few months of operation, doubling the current known population. While no near-Earth object is large enough to destroy the planet itself, asteroids of 1 mile or more in size can cause global catastrophes. For this reason, NASA has been tasked with detecting and tracking these large NEOs. As of 2021, NASA has detected over 90% of the largest objects, ensuring that none of them pose an immediate threat to Earth. However, smaller objects, while not as catastrophic on a global scale, can still cause significant regional damage. Take, for example, Apophis, named after the Egyptian god of chaos and destruction. It's a near-Earth asteroid that's captured the attention of scientists and the public. Discovered in 2004, this 1,000-foot wide or 304-meter wide asteroid initially caused concern because of calculations suggesting a possible collision with Earth in 2029. However, further observations have ruled out this possibility, confirming that Apophis will pass our planet safely. On April 13, 2029, Apophis will make an incredibly close approach to Earth, passing within 30,000 miles or 48,300 kilometers of our planet. By comparison, this distance is closer than the orbits of our few high-altitude satellites. This close pass provides a unique opportunity for scientific observations and research. During the flyby, the asteroid will become visible to the naked eye in some regions, appearing as a bright, moving point of light. This rare event will allow scientists to study its size, shape, and composition in unprecedented detail. NASA's Goldstone Deep Space Communications Complex in California will play a crucial role in observing Apophis. Using radar, scientists hope to gather detailed information about the asteroid's surface features and rotation. In addition, the NEOWISE mission can provide additional observations by focusing on Apophis's surface roughness and composition. These data are invaluable as they'll help refine our understanding of near-Earth asteroids. NASA's OSIRIS-APEX spacecraft, formerly known as OSIRIS-REx, will make a close approach to Apophis during its shortest flyby. The mission's goal is to study the asteroid up close, providing detailed observations that ground-based telescopes cannot achieve. OSIRIS-APEX will collect data on the composition and surface structure of Apophis, as well as any changes that occur as it passes near Earth. The spacecraft's instruments will help determine the asteroid's internal composition, which will also contribute to our broader understanding of the formation and evolution of the solar system. The close passage of Apophis has also attracted the attention of international space agencies. Teams from all over the world plan to observe and study the asteroid using ground and space telescopes. As part of the Neolite project, researchers from the Julius Maximilians Universität in Würzburg have proposed several concepts for small spacecraft that could accompany Apophis during its flyby. One proposed mission includes a small satellite that would follow Apophis for 2 months, acquiring high-resolution images and measurements. Another concept combines a small satellite with the European Space Agency's planned Ramses mission, which would provide extensive scientific observations. Although the asteroid poses no immediate threat to Earth, its close approach in 2029 presents a great scientific opportunity. Studying this asteroid up close will greatly improve our planetary defense strategies. To protect Earth, scientists have developed several planetary defense mechanisms, each designed to prevent potential collisions. One of the main methods is the kinetic impact strategy. It involves sending a spacecraft that will collide with an asteroid at high speed, altering its trajectory. This method relies on momentum transfer to move an asteroid into a safer orbit. NASA's 2022 mission Double Asteroid Redirection Test, or simply DART, was the first test of this method. The DART target was a small lunar satellite, Dimorphos, orbiting a larger asteroid, Didymos. As a result of the collision, Dimorphos's orbit was successfully altered, providing valuable data for future missions. Another proposed method is the gravity tractor. This method uses the gravitational pull of the spacecraft to slowly change the trajectory of the asteroid over time. By maintaining a stable position near an asteroid, the spacecraft's gravity can gradually alter the object's trajectory. Although this method's still theoretical and hasn't been tested in space, it is a promising approach for dealing with potential threats identified in advance. In extreme cases, however, nuclear explosions could be used to deflect or destroy an asteroid. In this approach, a nuclear device is detonated at a safe distance from the asteroid, vaporizing part of its surface and creating a recoil effect that moves the asteroid off course. However, this method is controversial because of the potential risks and legal implications of using nuclear weapons in space. To prepare for potential asteroid impacts, international space agencies regularly conduct simulations and drills. These exercises help hone detection, tracking, and deflection strategies. Planetary defense is a global issue that requires cooperation and coordination among countries. For example, in 2021, NASA participated in an international planetary defense exercise organized by the International Asteroid Warning Network and the United Nations Office for Outer Space Affairs. The exercise simulated the detection of a fictional asteroid on a collision course with Earth, allowing participants to practice their response strategies. As we continue to develop and refine our planetary defense strategies, international cooperation, and technological advances, they'll all play key roles in protecting our world from space-based threats. These cooperative efforts are essential, especially as we learn more about the diverse nature of the objects that threaten us. Asteroids and comets are often viewed as different celestial bodies. Asteroids are like the rocky remnants of the early solar system, mostly from the belt between Mars and Jupiter. Comets, on the other hand, are aliens from the outer reaches of our system and are composed of ice, dust, and rocky material. However, there are also rare objects that blur the boundaries between these two categories, exhibiting characteristics of both. One such object is QN 173, discovered in 2005. This unique celestial body orbits like an asteroid, but behaves like a comet. Unlike ordinary asteroids, which are inert, QN 173 exhibits comet-like activity by ejecting dust and developing a long, thin tail as it approaches the Sun. QN 173 orbits the Sun every 5 years, spending most of its time in the outer part of the asteroid belt. However, as it approaches the Sun, it shows increased activity, similar to a comet. This duality makes 2005 QN 173 an interesting object for astronomers. In the summer of 2021, astronomers using the Asteroid Terrestrial Impact Last Alert System in Hawaii observed an object displaying a comet-like tail. Further observations by Lowell Observatory and the Zwicky Transient Facility confirmed this activity. The 450,000-mile or 720,000-kilometer-long tail suggests that the object is covered in icy material that sublimates when heated by the sun. It's this process that turns the ice directly into gas, releasing dust and creating the characteristic tail. Interestingly, the narrowness of the tail indicates that the dust particles barely leave the core at extremely slow velocities. This presents a mystery to scientists, as such slow velocities would not normally allow dust to escape the asteroid's gravity. One hypothesis is that the rapid rotation of the core may contribute to the dust ejection. In addition to unique objects such as 2005 QN-173, many other near-Earth objects pose a potential threat to our planet. The European Space Agency maintains a comprehensive risk list, cataloging objects with a non-zero probability of colliding with Earth. The list contains detailed information on the size, velocity, and collision probability of each object. It currently contains over 1,600 targets. The list of risks is sorted by the Palermo scale, a logarithmic scale that assesses the risk of collision based on an object's size, speed, and probability of collision. Objects with higher values on the Palermo scale pose a greater potential threat. Statistical analysis of these potentially hazardous asteroids shows that while most NEOs pose minimal risk, there are a few objects that require close observation. For example, the size and velocity of an asteroid have a very significant impact on its probability of impact and potential damage. Large asteroids, usually over 1 kilometer in diameter, are of particular concern because of their ability to cause global catastrophes. Fortunately, NASA and other space agencies have identified and tracked more than 90% of these large objects, ensuring that none of them pose an immediate threat to Earth. Smaller objects, while not as catastrophic, can still cause significant regional damage. Events such as the Chelyabinsk meteor in 2013 and the Tunguska event in 1908 demonstrate the potential danger of small asteroids. As we continue to discover and track NEOs and refine our planetary defense strategies, international cooperation and technological advances remain critical. By understanding the diverse nature of these celestial bodies and preparing for potential threats, we can protect our planet and ensure a safer future for generations to come. Imagine a single point, just a speck of light, hovering in an endless sea of darkness. It's not just a random dot, it's our home, Earth. But what if we told you that this dot is just a fleeting moment in a cosmic panorama so vast and complex that it defies human comprehension? Imagine a night sky decorated with stars, each representing a sun, many of which have their own planets. Now, multiply that image by 100 billion. Even in this case, you've barely touched the surface. Beyond our Earth, beyond our Sun, even beyond our galaxy, lies a structure so vast that everything you know seems like a single thread in an unfathomable cosmic web. The human mind, which is itself a marvel, struggles to grasp this scale. Our brains are built to comprehend the rises and slopes of mountains and the vastness of oceans. But how do we comprehend a structure that stretches billions of light years? Today, we're on a journey to explore these galactic threads, the sinews and muscles of the universe itself. We will venture into a realm of the almost incomprehensible, where even the speed of light seems pedestrian. Spiders weave intricate webs, thin but strong. each thread connected to the other in a complex pattern. Architects of nature create these webs to survive, capture prey, and probe the environment. Now, imagine a web woven not by spiders, but by the very fabric of space and time itself. A web that links galaxies, star clusters, and dark matter into a complex web. This is the cosmic web, the grand architecture of our universe. Each node you see here is not a single star or planet, but an entire galaxy, a colossal cluster of billions of stars, planets, and other celestial objects bound by gravity. But what gives this network this structure? The answer lies in something we can't even see: dark matter. Dark matter, which scientists believe makes up about 27% of the universe, acts as the framework on which this web is built. Although invisible, its presence is felt through the gravitational pull that determines the formation of galaxies and the paths they take. The cosmic web was not always as we see it today. It evolved over billions of years, beginning with tiny fluctuations in the density of the early universe. These fluctuations grew, pulled together by gravity, eventually forming the majestic filaments and nodes we now see. One of the most impressive examples of a galactic filament is the Great Wall of Hercules' northern corona. This colossal structure spans a distance of up to 23 billion light-years, making it one of the largest known structures in the universe. Understanding this network is not just an academic exercise. It's a quest to understand our place in the universe. Are we simply an accidental byproduct of cosmic evolution? Or is there a grander design at work here? Scientists use a range of tools to study this network, from telescopes that can see distant galaxies to simulations that model the behavior of dark matter. Each discovery is a piece of the puzzle, a thread of a story that spans the entire universe. Here it is, Earth, a pearl of blue and green, suspended in the vastness of space. A planet teeming with life, from microscopic to magnificent. It's easy to think of the Earth as the center of everything, but in the grand scheme of the universe, it's just a speck. In our solar system alone, Earth is only one of 8 planets orbiting the Sun, and yet it stands out for its unique ability to support life. The oceans, the atmosphere, the magnetic field. All these elements are in delicate balance. Zoom out even further, and our entire solar system becomes a tiny dot in one of the spiral arms of the Milky Way galaxy, a galaxy that's home to hundreds of billions of stars, each potentially containing its own system of planets. In the Milky Way, it's just one galaxy in a cosmic web of hundreds of billions of galaxies. Each of these galaxies is a node, a focal point in this unimaginable structure. Even within our galaxy, the Earth is influenced by forces beyond its control. Dark matter, the invisible backbone of the cosmic web, shapes the structure of the galaxy and, as a result, the environment around the Earth. Yet despite its seemingly insignificant place in the cosmos, Earth is unusual for one reason: it has life. It's the only known celestial body where life not only originated, but has evolved to an incredible level of diversity and complexity. Humanity's quest to understand its place in the universe has led to remarkable scientific advances. Telescopes peer into remote corners of the universe, and supercomputers simulate the cosmic web, helping to answer fundamental questions about the nature of reality. For example, look at the Sun, the blazing ball of plasma that lights up our sky and warms our planet. It's the reason you can see these very images, the reason life exists on Earth. But in the context of the cosmic web, the Sun is just one node, a lone star among countless others. Close to the Sun, we find other stars, some smaller and cooler, others larger and hotter. Each of these stars is like a bead on a huge cosmic thread, linked together by gravity and dark matter. Our Sun is located in the Orion sleeve of the Milky Way, a small spiral arm located about 27,000 light-years from the center of the galaxy. Even within our galaxy, it is far from special, just one of about 400 billion stars. In the great expanse of the cosmic web, stars like our Sun form complex nodes that connect larger structures, such as galaxies and galaxy clusters. They are the building blocks, the fundamental units that give the web its shape. So what powers this celestial beacon? The answer is nuclear fusion. Deep in the Sun's core, hydrogen atoms collide and fuse to form helium, releasing massive amounts of energy. This energy not only powers the Sun, but also balances the gravitational forces trying to compress it. This energy has far-reaching consequences. It provides the Earth with the heat and light necessary for life. It drives our weather systems, powers photosynthesis, and even influences Earth's climate over the long term. Understanding the Sun is crucial to understanding the cosmic web. Various missions, such as the Parker Solar Probe and the Solar Dynamics Observatory, have been launched to study the Sun's behavior. These missions provide insights into solar cycles, magnetic fields, and even the future of the Sun. Although the Sun serves as a vital node in the cosmic web, nourishing life on Earth and influencing our local space environment, it's just one example in a universe teeming with stellar diversity. Every star, regardless of its size or lifespan, plays a role in shaping the cosmic web. From the tiniest red dwarfs to the massive blue giants, each star is a unique knot contributing to the overall structure of galactic filaments. Stars are often classified by their mass and brightness and plotted on a graph known as the Hertzsprung-Russell diagram. This diagram shows the life stage of a star and gives clues about its future fate. Take, for example, a red dwarf, the most common type of star in the universe. They're small, cold stars, also called M-type stars. Often less than half the mass of our Sun, they make up for their lack of size with longevity, burning for tens to hundreds of billions of years. Red dwarfs are frugal. They turn hydrogen into helium much more slowly than larger stars. This slow lifestyle allows them to be among the longest-lived objects in space. Now compare that to O-type stars, the rare titans of the stellar world. These stars are more than 15 times more massive than the Sun and can be 1,000,000 times brighter. Yet they live fast, die young, often in spectacular supernova explosions. O-type stars dramatically end their lives. They collapse under their own gravity and then explode as supernovae. These explosions scatter elements such as carbon, oxygen, and iron into space, promoting the formation of new stars and planets. Star clusters are like cosmic nurseries, places where stars of different types are born. These clusters serve as nodes in the cosmic web, linking different regions of the galaxy and even connecting galaxies to each other through filaments. Computer simulations help astronomers understand how different types of stars contribute to the cosmic network. These virtual models can simulate billions of years of cosmic evolution in a matter of weeks, showing how stars serve as the building blocks of larger cosmic structures. So, we've already found out, stars are not eternal. They are born, live, and eventually die. The life cycle of a star is a cosmic journey spanning billions of years, a journey that plays a key role in the evolution of the universe and the structure of the cosmic web. The birth of a star is a spectacle of cosmic proportions. It begins in a nebula, a vast cloud of gas and dust. Gravity pulls these particles together, getting denser and hotter until nuclear fusion ignites. A new star is born. Once a star reaches the main sequence stage, it enters a period of relative stability. The hydrogen in the core turns to helium, releasing energy that balances the gravitational forces trying to compress the star. This is the longest phase of a star's life, and it's where our sun is now. But even stars like our sun must face change. In about 5 billion years, the sun will run out of hydrogen fuel. Its core will shrink, but its outer layers will expand, turning it into a red giant. This phase is the prelude to the final fate of the star. Depending on its mass, the star will meet one of several ends. Stars with less mass, such as our sun, will shed their outer layers, leaving behind a white dwarf. More massive stars may undergo a supernova explosion, resulting in a neutron star or black hole. These deaths are not in vain. The death agonies of stars scatter important elements into space, elements that will become the building blocks of new stars, planets, and even life. Thus, the life and death of stars is an integral part of the cycle of cosmic creation and destruction. The cosmic web, from individual stars to entire galaxies, is a complex network of interconnected structures. But what binds these galaxies together? What are the threads that weave the complex fabric of the universe? The answer lies in galaxy clusters. Galactic clusters are massive collections of galaxies bound together by gravitational force. They may contain only a few or thousands of galaxies and often span millions of light years across. Just as dark matter plays a role in individual galaxies, it also acts as an invisible glue in galactic clusters. Even though we can't see it, we know it exists, holding the cluster together and forming its overall structure. Within a cluster, galaxies are not static. They are in constant motion. Some of them may be heading toward the center of the cluster, while others may be on their way to its edge, under the influence of complex gravitational interactions. Sometimes these interactions can lead to dramatic events, such as galactic collisions. When galaxies collide, their stars, gas, and dark matter merge to form a new, larger galaxy. These events are crucial to the evolution of galaxy clusters, and, by extension, the cosmic web. But clusters are not the end of the story. They often cluster together to form superclusters, which are among the largest known structures in the universe. These superclusters serve as the main nodes of the cosmic web, linking numerous clusters and filaments. Understanding galaxy clusters is the key to unlocking the mysteries of the cosmic web. They serve as threads connecting galaxies, forming the paths along which matter and energy flow on cosmic scales. Having studied the colossal structures of galactic clusters, the threads that weave the cosmic web, we now turn our eyes to an even more mysterious phenomenon. What if there were actual threads, strings of pure energy that stitch together the fabric of the universe? These hypothetical one-dimensional defects in space-time could be the loose threads of the universe, remnants of the first moments after the Big Bang. Imagine the universe just moments after the Big Bang, a hot, dense state of pure energy. As the universe cooled and expanded, this energy condensed into matter and structure. However, not everything went smoothly. In some regions, kinks occurred, leading to the formation of cosmic strings. Cosmic strings, if they existed, would be unimaginably thin but incredibly dense. A string less than an inch wide could weigh as much as the Earth. They would stretch across the vast expanse of the universe, perhaps even from one end to the other. Because of their enormous mass, cosmic strings would exert a strong gravitational pull, affecting the motion of galaxies and even bending light. They could serve as cosmic highways, directing the flow of matter and energy through the universe. The search for cosmic strings continues. Scientists are using a combination of theoretical physics and observational astronomy to search for these elusive structures. If the existence of strings is confirmed, they may become the missing links that will help us understand not only how the universe is organized, but also why it is organized this way. However, let's return to structures of unfathomable scale. Superclusters. They are the gravitational anchors that hold together vast networks of galaxies and galaxy clusters. Imagine moving away from our Milky Way galaxy, past our local group of galaxies, and even beyond our local Virgo supergroup. You'll find a network of superclusters, each containing hundreds to thousands of individual galaxies bound together in a complex dance of gravity. The superclusters are unevenly distributed. They form a kind of cosmic skeleton around which galaxies and galaxy clusters are located. This skeleton gives the cosmic web the shape that defines the large-scale structure of the universe. Within the supercluster, galaxies and clusters are in constant motion under the influence of the collective gravitational pull of the entire structure. This dynamic flow of matter and energy is what keeps the cosmic network alive and ever-changing. Among the most intriguing aspects of superclusters is the presence of gravitational anomalies like the Great Attractor. These are regions with such a strong gravitational pull that they influence the motion of the entire supercluster, serving as the pivots of the cosmic web. Understanding superclusters is crucial to cosmology. They serve as the largest laboratories for studying the expansion of the universe, the distribution of dark matter, and even the mysterious force of dark energy. The observable universe is estimated by scientists to contain 2 trillion galaxies. And yet, what we can see represents less than 5% of the universe. Standing over the precipice of cosmic understanding, we are humbled by the scale and complexity of the universe. From the smallest particles to the largest galactic filaments, each element serves as a piece of the puzzle. Here we are, a pale blue dot, a mere speck in the cosmic web. Yet, it is from this vantage point that we've begun to unravel the deepest mysteries of the universe. Armed with telescopes capable of looking billions of light years away, we become not just spectators, but active participants in this cosmic journey. And each new discovery is a step towards the answer to the eternal question that prompts all of us to ponder: what other mysteries does the universe hold that we have yet to unravel? The solar system has served as a reliable bulwark for life. But one day, humanity will have to leave its native Earth to continue existing. In recent decades, scientists have been desperately looking into the dim depths of space in search of a haven for life. So far, none of the exoplanets we've found have refuted the hypothesis of the uniqueness of life. But what if we're simply looking in the wrong place? Perhaps it's not the planets that hold all the answers, but their moons. In the mystical deep space, exomoons are unlike any other satellite in the solar system. The size of our Earth, these hidden giants have an amazing feature. Life can be found in their interior, many times more often than on ordinary exoplanets. Today, we'll dive into the mysterious, distant universe and try to discover why exomoons may someday change humanity. Let's go back to the very beginning of the history of exoplanet science. Since astronomy received a strong impetus only in the middle of the 20th century, scientists began to study the first exoplanets not so long ago. The first confirmed exoplanets were recorded in 1992. It was a group of Earth-mass planets orbiting the pulsar PSR B1257+12. Just 3 years later, scientists found the first planet orbiting the star 51 Pegasi, similar to our Sun. This was the birth of exoplanetary science, which is dedicated to the study of planetary systems outside our solar system, and, in addition, the search for places where human-like life could originate. Other exoplanets available in our visible universe didn't have to wait long either. In the following years, astronomers found several more exoplanets, until in 2009, the Kepler Space Telescope was sent to explore outer space. In just 5 years of operation, it was able to confirm about 715 exoplanets, with a size and conditions similar to Earth's. As of now, we already know about more than 5,500 planets outside the solar system, and the recently sent James Webb Telescope will likely to be able to show us even more distant planets. Further, in 2013, scientists were able to determine the planet's color for the first time, and a year later, they were able to record the magnetic field, and later, volcanic activity. Finally, in 2018, astronomers made a new, potentially breakthrough discovery. For the first time, a possible exomoon was recorded near the planet Kepler 1625b. While this may not seem like such an incredible discovery at first glance, exomoons open a new chapter in modern astronomy, not only as novel, hitherto unexplored space objects, but also as potential elements for supporting life on exoplanets and satellites themselves. Every year, knowledge about distant, dim exoplanets deepens, bringing scientists closer to a complete picture of the history of the entire universe. But how did the scientists manage to confirm so many planets in such a short time, when it's impossible to take a photo of each one? Only 69 planets were found with images. The most popular method is the transit method, which you may already know. When an exoplanet passes by its central star, the same star becomes slightly dimmer, which reveals the presence of an object orbiting it. Although this method doesn't allow us to directly observe the planet, and may turn out to be just a glitch, it is currently the most effective of all. Exoplanet exploration plays a crucial role in all of astronomy and the future of all of humanity. Exomoons, as a new chapter in exoplanet science, may have great potential for the search for extraterrestrial life. However, despite this, exosatellites are of not much interest to current research. The main problem associated with the search for these exoplanets is their elusiveness to telescope radar. Although no scientists deny that some exoplanets may have satellites, it's an extremely difficult and, to some extent, even impossible task for our current technologies to investigate them. The transit method, or more precisely, the method of studying the shift in the spectrum of stars, can confirm an exoplanet. But a satellite orbiting it? Almost under no circumstances, unless, for example, the spacecraft is in the closest possible proximity to the object of observation due to a completely insignificant change in the brightness of the star. Thus, even the very first exomoon found by Kepler and the ones discovered later near the planets Kepler 1708b and Kepler 1513b are still not perceived as full-fledged proof of their existence, and therefore there is a possibility that it could be just some kind of technical error during the observation, which is not so far from the truth, since further observations did not yield any encouraging results. However, as in the case of the giant planet's satellite Kepler 1625b, an exomoon can be seen if it is large enough. So far, the first hypothetical exomoon could be the size of the Earth and have a strange tilted orbit like Neptune's moon Triton. Such a huge size of a possible moon may become one of the most important elements in the further search for other moons. Thus, more than 20 exomoon candidates are currently known. All of them are gigantic. Probably at least for Kepler 1625b, it's the star around which it orbits. It is a red giant. This dying star can heat the moon's atmosphere, increasing its effective diameter and allowing scientists to detect satellites more often. However, perhaps right now, exomoons are not of too much scientific importance for scientists to invest a lot of resources in developing technologies to find them. At this stage of our science, exomoons don't seem to be a higher priority than other space objects, such as exoplanets. The satellites of distant planets are too complex to study and have a very high chance of a false positive result. Therefore, it may take months or even years of observation and analysis to confirm one satellite, when it seems more rational to spend this resource on exploring a planet with potential support for life, including human life. Of course, it is possible that exomoons may hide life in their interior, but alternatives in the form of rocky exoplanets like Earth are still of much higher importance in scientific circles. But we're going to focus on the exomoons themselves and try to investigate them. Is there any need to study these mysterious and hidden moons at all? In fact, these moons contain a lot of information for our complete understanding of the structure of the universe. But this will only be possible in the future, albeit not in the near future. The first thing that draws scientists' attention to even just candidates for exomoons is their size. The largest moon in the solar system, Ganymede, orbiting Jupiter, has a diameter of 3,273 miles, or 5,268 kilometers. But recorded exomoons can reach the size of the Earth, or even Neptune. Therefore, since such moons are even difficult to distinguish among exoplanets, it's incredibly exciting to imagine what moons might look like and what activity they exhibit. It's possible that some large exomoons have many of the features of planets, and that their study could overturn everything we know about satellites. Their similarities to other exoplanets, such as their likely geologic activity, bring us to the next important point for careful study in the future, and that is the support of life. We know that several moons of the solar system, such as Enceladus or Europa, despite their low surface temperatures and small size, could, hypothetically, be a haven for living organisms due to the presence of global oceans. However, what about the much more massive moons, which not only can support a dense atmosphere, but also have more access to building chemicals, both from the inside and outside? According to a study by the University of Washington, exomoons have more potential to support life than even exoplanets. They also have a habitable zone, although it's slightly different. But the main argument for exomoons as one of the most intriguing places for life to exist is the availability of several heat sources for them. The first source is the star itself, and the second is their planet. The moons are heated by the gravitational pull of the planet, which keeps the probable water in the interior of the moon in a liquid state. Moreover, heating from an exoplanet can stimulate geological activity, such as volcanic eruptions, creating enough gas inside the moon to maintain an atmosphere for a long time, and also bringing various crucial chemical elements to the surface. So exomoons are not as simple as they may seem. Perhaps the difficulty of finding them will be rewarded with a potential breakthrough in science. Finally, exomoons may become the necessary tool to study the formation of our universe. Thus, the analysis of exomoons near different stars and planets can reveal to scientists how space objects are formed, what factors are responsible for supporting life, and what the history of other planetary systems is in general. In particular, comparing the moons of the solar system with those of distant systems can give scientists an understanding of the specifics and conditions of their development, as well as an approximate value of the abundance of systems where complex intelligent life has developed. The Earth, hypothetically, may be almost the only planet on which life could have formed, at least in the visible universe. And any clues on exomoons with potentially higher chances of supporting living organisms can confirm or deny this. However, for now, deep exploration of exomoons is only a matter of the future. On the other hand, the James Webb Space Telescope mission will continue for several more years, so perhaps the hope of finding an exomoon for the first time in this decade is not going away. Nevertheless, since the search for exomoons is an extremely difficult and almost impossible task for our current technologies, exomoons are likely to become one of the drivers of technological progress. As we know, the transit method or gravitational lensing will not help to look for micro signs of the presence of exomoons, so this factor is already challenging scientists to modify or even create new technologies to capture such subtle objects. But this is a task for the near future. In the long term, both intriguing moons and exoplanets will require much more thorough analysis, including using images and samples of the atmosphere or even soils. So, if interesting candidates where extraterrestrial life exists are ever found, then comprehensive space missions are likely to follow, advancing human knowledge of the research focus. The only step we have left to take is to find such an exoplanet or exomoon. In 2026, the European Space Agency plans to send the Plato mission, which will continuously look at several areas in outer space to capture transiting objects. The mission will last for 6 years and may be the one to make this expected discovery. However, the benefits of exomoon search and exploration do not end with a technological breakthrough. Exomoons are very valuable natural laboratories located near various planets and stars. Analyzing the impact of these bodies on the moons will not only deepen what's known about the formation of planets, but also demonstrate to scientists the variety of conditions under which life can develop. For example, traces of bio or even technosignatures created by civilizations on various moons can provide a clearer picture of the signs for the development of intelligent life, thus building more prioritized paths for future missions to the most likely planets or moons for aliens to live on. But for now, we can only wait for the moment when we find the first exomoon and begin a long but life-changing scientific and technological ascent. Exomoons, despite their invisibility and skeptical insignificance, may one day critically change everything known to the entire human race about our vast universe. Even a small observation can eventually become the main driver for revolutionary discoveries. Continued research will reveal more and more answers, and only by pursuing this knowledge will the cumbersome, mysterious cosmos one day become less confusing to us. But in the face of the vast universe, we must never lose our enthusiasm for learning, no matter how difficult and distant our desired outcome. Imagine a colossal invisible force at the galaxy's heart, controlling its existence. This hidden conductor is none other than a supermassive black hole. Although they're often portrayed as chaotic, all-consuming monsters, these giants play a crucial role in the life cycle of galaxies. At the center of most large galaxies is a supermassive black hole whose gravitational pull is so strong that not even light can escape it. However, they actually do more than just absorb matter. They act as the heart and lungs of their galaxies, breathing life into the celestial environment in ways that are only beginning to be understood. Recent research shows that the jets of gas and radiation ejected from the poles of supermassive black holes are akin to the airways that feed our lungs. These jets create shock waves that oscillate, much like the thoracic diaphragm in our chest cavities, which moves to inflate and deflate our lungs. This respiratory system helps regulate the growth of galaxies, preventing them from getting too big and ensuring a delicate balance in the cosmic ecosystem. A simulation shows how a galaxy's heart and lungs in the form of gas plumes from a central supermassive black hole can prolong its life. If these supermassive black holes did not act as galactic regulators, the universe would be filled with zombie galaxies, huge clusters of dead or dying stars. The shock waves generated by black hole jets can prevent star formation by heating the surrounding gas, preventing it from cooling and condensing into new stars. This process may seem destructive, but it's necessary to maintain the health and longevity of galaxies. Today, we'll try to understand the mysterious nature of supermassive black holes, learn the profound impact they have on the universe, and by the end, we'll realize that even in the darkest corners of the cosmos, there is a heartbeat that connects us all. To fully understand the impact of black holes on galaxies, we need to understand their formation, types, and some key discoveries. Black holes can form in two main ways. The most common way is associated with the death of massive stars. When a star with a mass of about 8 to 10 times that of our Sun exhausts its nuclear fuel, a catastrophic explosion, known as a supernova, occurs. The core collapses under its own gravity, forming a stellar mass black hole. Such black holes usually have a mass several times that of the Sun. Another way is the direct collapse of massive gas clouds, which completely bypasses the star formation stage. This process can lead to the formation of black holes with masses from thousands to hundreds of thousands of solar masses. Such direct collapses are thought to have occurred in the early universe, and were the seeds of the supermassive black holes we see today. The concept of black holes was first predicted by Carl Schwarzschild in 1915 as an exact solution to the equations of Einstein's general theory of relativity. These equations describe how matter forms the fabric of space and time. Schwarzschild's solution allowed us to discover regions where gravity is so strong that nothing, not even light, can escape it. The first black hole confirmed by observations was Cygnus X1. Discovered in 1964, this stellar mass black hole in the Milky Way was identified by X-ray emission that was caused by the accretion of material from a companion star. This discovery was the first convincing evidence that black holes are not just theoretical constructs, but real objects in the universe. Scientists have determined that a black hole consists of three main regions: the event horizon, the photon sphere, and the singularity. The event horizon is the boundary beyond which nothing can go once within its limits. The photon sphere is a region where gravity is so strong that light particles are forced to orbit. In the center, there is a singularity, a point of infinite density where the laws of physics known to us are destroyed. Black holes come in a variety of sizes. Stellar mass black holes are formed from collapsing stars and have masses several times that of the Sun. Supermassive black holes, located at the center of most galaxies, have masses ranging from millions to billions of solar masses. Intermediate mass black holes, which are less common, fall between these two categories and have masses between 100 and 100,000 solar masses. The 2019 Event Horizon Telescope collaboration has captured the first ever image of a black hole located in the galaxy M87. In this historic image, the black hole's shadow can be seen against a glowing accretion disk. The observation provided direct visual confirmation of theories about black holes and opened new possibilities for studying these mysterious objects. One of the most common and debated questions about black holes lately is whether they die. According to Stephen Hawking's theory, black holes can slowly evaporate over time through a process known as Hawking radiation. This occurs when pairs of virtual particles form near the event horizon, one falling into the black hole and the other flying out. Over an incredibly long period, this trickle of ejected particles can cause the black hole to lose mass and eventually vaporize. Although black holes are portrayed in science fiction, they're not cosmic vacuum cleaners that indiscriminately suck up everything around them. To hit them, objects must come incredibly close to the event horizon. In addition, although black holes have been proposed as potential wormholes or portals to other universes, these ideas remain speculative and are not supported by any observational data. Scientists estimate that the Milky Way alone contains more than 100 million black holes. Understanding the basics of black holes, how they form, their different types, and key discoveries lays a solid foundation for studying their profound impact on galaxies and the entire universe. So, although supermassive black holes are invisible, their presence is felt due to the enormous gravitational forces they exert on their surroundings. But how do these colossal formations arise, and what are their defining characteristics? Theoretically, a black hole is formed when a significant amount of matter is compressed into an incredibly small space, creating a gravitational field so powerful that it cannot escape. This concept, once considered too fanciful to be real, is now an accepted reality. Black holes, especially supermassive black holes, are scattered throughout the universe, and their number may be in the billions. Supermassive black holes with masses millions or billions of times that of the Sun are detected due to their gravitational influence on nearby stars. These stars orbit around the black hole much faster than they would around a normal object of similar size. By measuring these orbital velocities, astronomers can estimate the mass of the black hole. For example, the black hole at the center of our Milky Way, Sagittarius A, has a mass of about 4 million solar masses. Some supermassive black holes exceed even Sagittarius A. The dwarf galaxy Leo 1 is home to a black hole with a mass of about 3 million solar masses. In the neighboring elliptical galaxy Centaurus A, there is another black hole with a staggering mass of 55 million solar masses. And even more colossal is a black hole in the Abell 2261 galaxy cluster, estimated to have a mass of about 100 billion solar masses, although its exact location remains unspecified. These black holes, especially in active galaxies, behave differently. Surrounded by an accretion disk of rapidly spinning gas and dust, they can emit huge amounts of energy, sometimes outshining their entire galaxy. This very process was famously captured by the Event Horizon Telescope in 2019, when it imaged the accretion disk around the supermassive black hole in Messier 87, revealing the ominous shadow of a black hole with a mass of 6.5 billion solar masses. The formation of these supermassive black holes is the subject of intense study and speculation. Unlike the vacuum cleaners of science fiction stories, real black holes attract matter by gravity rather than by active suction. This gravitational attraction becomes unusually strong at close distances, but at greater distances, it behaves like the attraction of any other object of similar mass. According to one theory, the oldest supermassive black holes formed almost immediately by the gravitational collapse of massive gas clouds, containing as much matter as millions of stars. This direct collapse model suggests that such black holes could have formed in as little as 150 million years, a blink of an eye by cosmic standards. According to another hypothesis, primordial black holes born under the stressful conditions of the Big Bang served as seeds for subsequent growth. By studying these colossal formations, we gain insight into the fundamental processes that shape galaxies and, by extension, the universe itself. But what happens when two galaxies collide? It's not just a dramatic cosmic event, it's a transformational process that changes the very fabric of the universe. At the center of these galactic collisions are the same supermassive black holes, and their interactions produce some of the most energetic phenomena known. When galaxies approach each other, their central supermassive black holes begin to interact gravitationally, spiraling toward an inevitable merger. This process is not silent. It sets in motion vast amounts of ambient gas and dust, creating a turbulent environment ripe for extraordinary phenomena. Physicists have modeled these colossal mergers and found that as black holes spiral closer together, they can produce incredibly energetic jets of electromagnetic radiation. They fly out along the axis of rotation much more powerfully than those typically observed around isolated black holes. The cosmic show begins even before the black holes fully merge, giving astronomers a potential warning of these events. When these supermassive black holes finally collide, their jets combine into single high-energy bursts. These may be accompanied by less directional bursts, increasing the chances of detection. The merger process sets the surrounding plasma in motion, causing powerful jets that can theoretically be observed from billions of light years away. The detection of these cosmic events is not just exciting, it provides a unique opportunity to test the limits of Einstein's general theory of relativity under extreme conditions. The observation of these mergers can either strengthen the current understanding of gravity or open up new physics, potentially leading to alternative theories. Future missions such as the Laser Interferometer Space Antenna, or simply LISA, promise to expand our ability to pinpoint these mergers. LISA, a joint effort between NASA and the European Space Agency, will orbit the Sun and detect gravitational waves emitted by such mergers. Combining gravitational wave data with electromagnetic observations will allow precise localization and detailed study of these energetic events. Until such advanced instruments become operational, astronomers rely on existing observatories to detect electromagnetic jets. They provide a dynamic view of galaxy evolution, demonstrating how such mergers can dramatically change the structure and behavior of galaxies. But let's take a closer look at Sagittarius A, which is 4.3 million times the mass of the Sun. In mid-spring of this year, the giant of our galaxy revealed new secrets, thanks to the advanced observations of the Event Horizon Telescope. For the first time, astronomers have recorded polarized light around Sagittarius A, providing new insights into the magnetic fields surrounding this black hole. Polarized light is crucial to understanding these fields because it shows how light waves are oriented and allows us to understand the properties of the gas and the mechanisms at work in powering the black hole. Interestingly, the magnetic fields around Sagittarius A are strikingly similar to those observed around the much larger black hole in the galaxy Messier 87, which has a mass of 6.5 billion times that of our Sun. This similarity suggests that strong organized magnetic fields may be a common feature of all black holes, regardless of their size. The presence of such magnetic fields makes the possibility that Sagittarius A may contain a hidden jet intriguing. In other black holes, these fields drive powerful streams of matter. Although Sagittarius A appears relatively quiet, consuming a minimum of matter, the similar structure of its magnetic field hints at the possibility of a weak jettison that has yet to be observed. This new image of a black hole at the center of the Milky Way tells us that there are strong, swirling, and ordered magnetic fields near the black hole, explains Sarah Issa-Un, study co-leader and NASA Hubble Fellowship Program Einstein Fellow at the Center for Astrophysics at Harvard and Smithsonian. These fields are crucial to how black holes interact with the gas and matter around them. It was the EHT, an array of telescopes around the world, that made these groundbreaking observations possible. By combining data from multiple telescopes, the EHT forms an Earth-sized virtual telescope capable of capturing unprecedented detail of black holes. Although Sagittarius A is closer to Earth, it presents a unique challenge because of its smaller size. The material swirling around it moves quickly, making it difficult to get clear images. In contrast, in the larger M87, the material moves more slowly, making it easier to observe. Overcoming these difficulties has provided invaluable data for comparing black holes at opposite ends of the mass spectrum. The observed similarity in the magnetic fields between Sagittarius A and Messier 87 suggests that the central black hole of our galaxy may possess a hidden jet. If such a jet exists, it would provide new insights into the behavior and evolution of black holes and the galaxies in which they reside. The observation of this jet would be a great discovery, linking Sagittarius A to the energetic processes that form galaxies. The discovery of such a jet will greatly expand our understanding of how black holes affect their surroundings. Jets can expel gas and dust, affecting star formation and the overall evolution of galaxies. By comparing different black holes, astronomers will be able to identify the universal principles that govern these mysterious objects. Studying our own supermassive black hole allows us to root these abstract concepts in a familiar context, bringing distant space closer to home. The influence of supermassive black holes extends far beyond their gravitational effects. Relativistic jets can have a dramatic effect on the formation and evolution of galaxies, affecting everything from star formation to the distribution of gas and dust. A striking example of the influence of black hole jets is the Teacup Galaxy, located at a distance of about 1.3 billion light-years from Earth. The Teacup Galaxy got its name because of its peculiar handle structure, which was formed due to the activity of a relativistic jet from its central supermassive black hole. This galaxy is a vivid example of how even low-powered jets can significantly affect the environment. Even in the case of radio-quiet galaxies, jets can redistribute and disrupt the surrounding gas, and this will have an impact on the galaxy's ability to form new stars. Recent observations with the Atacama Large Millimeter Array have shown that jets in the Teacup Galaxy, although relatively weak, move, heat, and accelerate the galaxy's gas. Even in the case of radio-molten galaxies, jets can redistribute and disrupt the surrounding gas, and this affects the galaxy's ability to form new stars, explains Cristina Raus Almeida, an astronomer at the Instituto de Astrofísica de Canarias. The effects of these jets do not always occur head-on. The study found that the most significant effects in the Teacup Galaxy occur perpendicular to the direction of the jets. This lateral turbulence is caused by shock waves generated by the jet bubble, which heats and inflates the gas. These interactions can prevent star formation by preventing the gas from cooling and collapsing into new stars. While strong jets can heat the gas in galaxies to such an extent that they slow its growth, preventing the formation of new stars, weaker jets, such as in radio-quiet galaxies, also play an important role. These jets can still stir up the gas in a galaxy, causing it to move and redistribute. Such activity can lead to the formation of new structures within the galaxy and affect its long-term evolution. Understanding the influence of these jets allows astronomers to piece together the complex puzzle of galaxy formation. Supermassive black holes are an integral part of the life cycle of galaxies, from the dramatic changes caused by powerful jets to the more subtle but significant effects of weak ones. Stay tuned to explore together the forces that shape our universe. Amidst the peace and tranquility of the celestial bodies of the solar system, there is one object that greatly disturbs the peace of the rest: the Moon, Io. Unlike any other orbiting the mighty Jupiter, shrouded in mystery, Io is a world of fire and fury, a stark contrast to the icy moons and calm planets that share its cosmic neighborhood. This mysterious moon, the most volcanic body in our solar system, is a testament to the dynamic forces at work in the cosmos. Its surface, riddled with hundreds of active volcanoes, tells the story of the relentlessly complex gravitational pull of Jupiter and other moons. Meet Juno, NASA's intrepid explorer, on a journey to this fiery world. Its mission is to unravel the mysteries of Io, capture its fiery essence, and uncover the secrets that have long lurked beneath its tumultuous surface. As Juno makes its closest approach in 2 decades, we stand on the threshold of new discoveries and are ready to unravel the mysteries of this volcanic moon. What will Juno tell us about Io's turbulent volcanoes? How does the turbulent nature of this moon affect giant Jupiter and its other moons? And what can Io tell us about the forces that shape our solar system? Let's find out. Discovering new space vistas, Juno, a spacecraft made not only of metal and circuitry but also of ambition and curiosity, is embarking on a journey that hasn't been taken in more than 2 decades. For the first time in 20 years, a spacecraft dares to come so close to Io that we can come face to face with a world of extreme volcanic activity. Juno's close approach is not just a routine flyby, but a bold dive into the unknown. The spacecraft, equipped with state-of-the-art instruments, is designed to withstand the harsh radiation environment of Jupiter and its moons. As it approaches the rough surface of Io at a distance of 930 miles, Juno's sensors come to life, taking high-resolution images and collecting valuable data. In late 2023, the probe made its closest flyby of Io, taking some incredible images in the process. In them, Jupiter's moon appears to glisten with sulfuric hues, and its surface is speckled with spots created by the ongoing volcanic activity that rages on it. By combining data from this flyby with our previous observations, the Juno science team is studying how Io's volcanoes vary, says astronomer Scott Bolton of the Southwest Research Institute. We are looking for how often they erupt, how bright and how hot they are, how the shape of the lava flow changes, and how Io's activity is connected to the flow of charged particles in Jupiter's magnetosphere. The heart of this mission lies in the technological prowess that Juno possesses. The spacecraft's JunoCam continues to take spectacular images despite the challenges of Jupiter's intense radiation. The Stellar Reference Unit's Stellar Navigation Camera is also a scientific instrument, providing the highest resolution images of Io's surface to date. On Earth, scientists are studying the data coming from Juno. Each byte of data is a piece of the puzzle, revealing new information about the volcanic nature of Io. Analyzing this is a window into our solar system's past, present, and future. So, late last year, NASA's Juno probe took the highest resolution images of this moon to date. Among these images, one that stands out is one taken on December 30th, which vividly depicts the volcanic nature of Io. This image, enhanced to emphasize details, shows a volcanic plume erupting from Io's surface, with plumes reaching more than 60 miles, given that the moon's diameter is about 2,200 miles. As Juno continues its journey around Jupiter, each orbit brings new opportunities, new challenges, and new discoveries. Among the planet's other 95 moons, Io stands out not only for its proximity to Jupiter, but also for the dramatic geologic activity that this proximity provokes. The volcanic nature of the moon is a direct consequence of Jupiter's enormous gravitational forces. Io is not a huge moon. It's only slightly larger than the one orbiting our planet. However, as the largest planet in our solar system, Jupiter has tremendous gravity. This enormous force stretches and squeezes Io, creating what is known as tidal heating. The satellite's orbit itself is not a perfect circle, resembling more of an ellipse, so the moon experiences varying degrees of gravitational pull from Jupiter. As it approaches Jupiter, the planet's gravity stretches Io, and as it moves away, it compresses it. This constant stretching creates tremendous internal heat within Io, leading to its intense volcanic activity. This JunoCam image captures a plume of material ejected from the unseen volcanic Prometheus. Indicated by the red arrow, the plume is just visible in the darkness below the terminator, the line dividing day and night. The image was taken by spacecraft on October 15, 2023. Tidal heating is so intense that it turns Io's interior into a bubbling cauldron of molten rock. This heat leads to the volcanic activity that defines Io's landscape. Hundreds of volcanoes dot its surface, some of them spewing lava fountains up to hundreds of kilometers high. There are about 400 active volcanoes on Io, about 150 of which are erupting at any given time. But Jupiter is not the only player in this gravitational confrontation. The other Galilean moons, Europa, Ganymede, and Callisto, also exert their influence on Io. Their gravitational attraction helps to maintain Io's elliptical orbit, thus playing a crucial role in the tidal heating process. This complex gravitational interaction is a perfect example of how celestial mechanics determine the fate of a moon. The tidal forces of Jupiter and its moons don't just heat Io, they create a world in which geologic activity is the norm, not the exception. Io, a moon shrouded in fire and brimstone, plays a key role in the grand theater of Jupiter's system. Its incessant volcanic activity not only shapes the landscape, but also significantly affects the very nature of Jupiter's magnetosphere. As we mentioned earlier, the volcanoes on this satellite are the most active in the solar system. In doing so, they spew huge amounts of sulfur dioxide, or SO2, into space. This outgassing, a direct result of intense internal heating, contributes to an atmosphere rich in sulfur compounds. But Io's influence extends far beyond its own atmosphere. As Io rotates within Jupiter's massive magnetosphere, sulfur dioxide and other volcanic gases ionize, becoming charged particles. These particles become trapped in Jupiter's magnetic field, forming a plasma torus along Io's orbit. This torus, a glowing ring of ionized particles, is a direct manifestation of the moon's volcanic power. The plasma torus is not a static feature. It changes in response to Io's volcanic activity. The ejection of material from volcanoes feeds the torus, affecting its density and composition. This complex interaction between Io's volcanism and the plasma torus illustrates the interconnectedness of Jupiter's system. It's also thought to be responsible for powerful, permanent auroras at the planet's poles. Volcanic emissions, once in the atmosphere, escape into space. Here they undergo rapid reneutralization, a process that ejects these particles at high velocity in a plane perpendicular to the local magnetic field. This phenomenon continues to the formation of extended sodium nebulae, adding another layer to the complex environment around Jupiter. Observational studies have been crucial in shedding light on these interactions. For many years, telescopes, like TRAPPIST, have followed the variability of Io's sodium cloud. These observations have shown that the physical properties of the sodium jets from Io are highly variable and, interestingly, do not always correlate directly with the global brightening of Jupiter's plasma torus or the extended sodium nebula. This study highlights the complexity of the surface-atmosphere-magnetosphere coupling in the Jupiter system. Current research aims to reveal the precise mechanisms by which Io's volcanoes supply material to the plasma torus, and how Io's sodium jet contributes to filling the plasma reservoirs of the magnetosphere. Thus, Io's relentless volcanic activity and its interaction with Jupiter's magnetic fields are not just isolated phenomena. They play a fundamental role in shaping the dynamics of Jupiter's magnetosphere, producing plasma structures and neutron clouds that are key to understanding the complexities of planetary magnetospheres. Ongoing research and observations allow us to separate the layers of these interactions, offering a deeper understanding of the workings of our solar system. As we look to the future of space exploration, the fiery moon Io appears as a beacon of mystery and potential. The next phase of Io exploration is poised to reveal secrets that have remained hidden beneath its stormy surface for centuries. Introducing the Jupiter Icy Moons Explorer mission, abbreviated as JUICE. JUICE aims to study Jupiter's icy moons, offering intriguing opportunities to further our understanding of Io. Although JUICE's primary focus is on Ganymede, Europa, and Callisto, its extensive suite of instruments can provide valuable insights into Io's dynamic environment. The interplanetary spacecraft was launched on April 14, 2023, from the Guiana Space Center in French Guiana by the European Space Agency. The spacecraft is expected to reach Jupiter in July 2031 after 4 gravity assists and an 8-year journey. As JUICE passes through the Jupiter system, its trajectory may provide opportunities to observe Io. These encounters may provide additional data on the satellite's volcanic activity and its effect on Jupiter's magnetosphere, complementing the conclusions drawn by missions directly targeting Io. Equipped with sophisticated instruments designed to study magnetic fields, plasma environment, and atmospheric composition, JUICE has the potential to indirectly expand our knowledge of Io. By studying Jupiter's magnetosphere and the interactions within it, JUICE can provide a broader context for the satellite's role in the entire Jupiter system. Another mission, Io Volcano Observer, or IVO, is a bold initiative that represents the next leap in our quest to understand this volcanic moon. IVO is a mission designed to study Io's intense volcanic activity, its subsurface structures, and the complex processes that drive its geologic dynamism. IVO's mission is to enter orbit around Io and make multiple close flybys. Equipped with state-of-the-art instruments, IVO will map Io's volcanic heat flows, study lava composition, and probe the moon's internal structure. This mission aims to answer fundamental questions about the mechanisms of volcanism on Io and the role of tidal heating in its activity. One of the most interesting aspects of the IVO mission is exploring the bowels of the moon. What lies beneath its fiery facade? IVO seeks to shed light on this mystery by studying the moon's internal structure. Seismic measurements and magnetic field analysis may reveal the presence of subsurface magma chambers and provide insight into the Moon's volcanic flow system. The potential for new discoveries about Io's volcanic mechanisms is enormous. IVO observations could revolutionize our understanding of volcanic processes, not only on Io, but throughout the solar system. By studying Io's unique volcanism, we'll be able to gain insight into the thermal evolution of planetary bodies and the role of tidal forces in shaping planetary geology. In the meantime, Juno continues to work, with many more observations planned, not only of Io, but also of the other Galilean moons, and, of course, Jupiter itself. The spacecraft will continue to operate until September 2025, or until it breaks down, whichever comes first. In the meantime, we'll look forward to more images taken by the next flyby. Imagine a canvas of moments woven with the threads of time. Matter that stretches endlessly in all directions, capturing every choice, every event, every heartbeat. What if you could navigate this intricate fabric? What if you could go back in time, look into the future, or even change the course of history? Time. It governs our lives, but it remains one of the most mysterious phenomena in the universe. We measure it, we chase it, but can we control it? The concept of time travel has intrigued humanity for generations, inspiring countless works of fiction and sparking rigorous debate. But what can science say? Can time travel ever move from the pages of science fiction to the annals of scientific fact? Einstein's theory of relativity opened the door to this possibility by suggesting that time is not a constant, but a variable that can be manipulated. In addition, there are black holes, cosmic phenomena so powerful that they can distort not only light, but time itself. Did you know that astronauts aboard the International Space Station age slower than humans on Earth, even if only by a fraction of a second? This is not science fiction. It is a proven consequence of traveling at high speeds. So let us journey through the corridors of time. We'll explore the science, paradoxes, and limitless possibilities that may one day make time travel a reality. Welcome to a journey through time. Long before the advent of science as we know it, humankind was fascinated by the heavens and the passage of time. Ancient civilizations paid attention to the stars, sun, and moon, creating elaborate calendars and methods of measuring time. Transported to the modern era, this fascination has found a new canvas: film and literature. The concept of time travel has been a recurring theme, offering both escapism and a platform for intellectual curiosity. In 1895, H.G. Wells wrote the novel The Time Machine, which, by the way, not only popularized the term time machine, but also introduced the idea that time could be navigated like the dimensions of space. Then came Back to the Future, a pop culture powerhouse that took the concept of time travel and made it accessible to a whole new generation. Who could forget the DeLorean, the magnetic condenser, the flux capacitor, and Doc Brown's charming eccentricity? But it's not just a Western phenomenon. The allure of time travel knows no cultural or linguistic boundaries. From the Japanese Steins Gate to the Soviet Ivan Vasilievich changes profession, the theme of time travel resonates around the world. So what is it that attracts storytellers to this concept? The allure of rewriting history? The excitement of the unknown? Or perhaps the philosophical questions such journeys raise? It's a desire fueled by a mixture of nostalgia and anticipation, a longing to revisit cherished memories or leap into the promises of tomorrow. And as we stand on the cusp of scientific discoveries that could turn dreams into reality, the question becomes more important than ever. Could we? Should we? And what if we did travel through time? The blackboard is the canvas on which the abstract becomes possible. Here, equations like E equals mc squared are not just symbols. They're keys to understanding the universe. But can they unlock the secrets of time travel? From silver screens to living room TVs, time travel has been portrayed in countless ways, But let's peel back the layers of fiction and delve into the science that can make time travel more than just a plot device. Meet space-time, the four-dimensional fabric of our universe. According to Einstein's theory of relativity, this fabric can be bent and deformed by mass and energy. But can it be torn or twisted to create a path through time? Time dilation, a consequence of Einstein's theory, suggests that time can flow at different rates depending on the speed of motion or the gravitational field. For example, astronauts on the International Space Station age slightly slower than people on Earth. Experiments with particle gas pedals and atomic clocks have provided empirical evidence of time dilation. It's been observed that particles traveling near the speed of light decay more slowly than their stationary counterparts. In addition, there are wormholes, hypothetical tunnels in space-time that could theoretically allow time and space to be shortened. Although somewhat speculative, the math suggests that they are possible. Leading physicists and cosmologists have voiced their opinions on the matter, offering theories that range from plausible to downright bizarre. Some even suggest that quantum mechanics, the science of the very small, may play a role in making time travel possible. And let's not forget black holes, the mysterious titans of space. Their enormous gravity is so strong that it distorts not only space but time itself. Could these cosmic phenomena be a gateway to other times? The scientific community is far from consensus. Time travel raises questions that challenge the very foundations of physics, from the nature of reality to the concept of causality. They say time goes forward, always forward, and never backward. But what if we could leap forward, skipping years, decades, or even centuries? The idea might not be as far-fetched as it seems. When it comes to slowing down time, speed becomes the main parameter. According to Einstein's theory of relativity, the faster you move in space, the slower you move in time. So, could extreme speed be our ticket to the future? Believe it or not, time travel to the future has already been done, albeit on a minuscule scale. Astronauts aboard the International Space Station experience time dilation and age a little slower than their counterparts on Earth. Let's turn our attention to the twin paradox, the famous thought experiment that takes time dilation to a new level. Imagine twins separated at birth. One travels through space at near light speed, while the other remains on Earth. Upon reunion, the space twin will appear younger. Achieving speeds close to the speed of light would greatly enhance this effect. However, such speeds are currently beyond the reach of our technology. Not to mention the energy requirements would be astronomical. Scientists and engineers are wrestling with these problems, researching propulsion technologies that could, one day, make near light speed travel possible. But even then, can the human body withstand such a journey? Imagine a future where time dilation capsules are as common as airplanes, allowing people to jump into the future to glimpse advanced civilizations or even avoid catastrophes. Will knowledge of the future be a gift or a curse? And what will it mean for the concept of free will? From science fiction to science articles, wormholes have captured our collective imagination. These hypothetical tunnels in the fabric of space-time may turn out to be the cosmic shortcuts we've been dreaming of. But what are wormholes, and could they be the key to time travel? Imagine folding a piece of paper so that 2 points touch, and then poking it with a pencil. In space-time, the wormhole would be that pencil, creating a straight path between 2 distant points. This concept gained traction in the scientific community thanks in part to Carl Sagan. While writing his novel Contact, he consulted with physicist Kip Thorne to explore the scientific possibility of using a wormhole for interstellar travel. Today, physicists are delving deeper into the math of wormholes. While the general theory of relativity allows for their existence, the equations also assume that they collapse too quickly for anything to pass through them. Theoretically, by introducing some exotic matter, for example, it could counteract the gravitational forces causing the wormhole to collapse, keeping it open long enough for something or someone to pass through. The portrayal of wormholes in popular media often glosses over these complexities. They're usually portrayed as stable, luminous vortices. But the reality, if they exist, can be much more volatile and unpredictable. Despite the lack of empirical data, the study of wormholes is a dynamic area of research. Scientists use computer modeling and indirect observations to understand their properties and potential uses. Imagine the possibilities if wormholes could be used for time travel. One end could be anchored in the present, the other in the future or the past. The implications for research and even for preventing global catastrophes are staggering. Wormholes open the door to questions not only about where we might go, but when. And as we approach the potential discovery of these cosmic shortcuts, we must ask ourselves, are we ready for the responsibility associated with such power? In the world of the very small, where particles are also waves, and reality itself seems blurred, lies the quantum world. Could this region of uncertainty hold the keys to unlocking time travel? Quantum mechanics challenges our everyday understanding of the world. Take the two-slit experiment, in which particles behave as both particles and waves. This duality suggests that, at the quantum level, the fabric of reality is much more malleable than we thought. Great minds like Richard Feynman and Niels Bohr have delved into the mysterious world of quantum mechanics, a theory that's been incredibly successful in explaining the behavior of matter and energy at extremely small scales. Some physicists suggest that quantum mechanics may offer a basis for time travel. Quantum tunneling, for example, allows particles to pass through barriers as if they're ghosting through walls in the two-slit example. Can a similar principle enable time tunneling? Quantum computing is a new field that uses the principles of quantum mechanics to perform calculations at speeds unimaginable to classical computers. Some speculate that quantum algorithms could solve equations related to time travel that are currently too complex for today's computing machines. The concept of quantum entanglement adds interest. Imagine two particles cooked together in a certain way. Once entangled, these particles become interconnected, forming a single quantum system. The truly stunning aspect of entanglement is that the state of one particle instantly affects its entangled partner, regardless of the distance separating them. This could be across the room or even across the galaxy. Change the spin of one, and the other instantly changes. Albert Einstein famously called it spooky action at a distance. At first, he didn't like this idea because it seemed to violate the limit of the speed of light set by his theory of relativity. Since then, however, numerous experiments have confirmed that entanglement is a real and fundamental aspect of quantum mechanics. Could such an effect at a distance make a difference to instantaneous time travel? While the intersection of quantum mechanics and time travel is still in the realm of speculation, it is a hotbed of scientific research. Researchers are studying everything from quantum loops in time to the role of quantum gravity in the early universe. Imagine a future in which the principles of quantum superposition could account for multiple timelines or realities. What if you could exist in a superposition of past and present? Could quantum mechanics be the final piece of the puzzle in our quest to conquer time? Moving on, let's move from the world of the microscopic scale to the grandiosely large one, black holes, mysterious titans of space whose gravity is so strong that not even light can leave them. But could these celestial phenomena hold the secret to time travel? Enter the concept of closed time-like curves. A closed time-like curve, or CTC, is a path in spacetime that loops back on itself. Theoretically, an object or even a person traveling along a CTC could end up in an earlier point in time. The idea was first proposed by physicist Kurt Gödel in 1949. Gödel's solution to Einstein's field equations suggested that rotating universes could contain paths looped in time. However, these solutions required certain conditions, such as a universe filled with rotating matter. Although Gödel's model is considered physically implausible in most cases, it has opened the door for other scientists to explore the concept. The main challenge is to find a scenario in which STSSs could exist without violating the laws of physics. One such scenario involves rotating black holes, known as Kerr black holes. Massive gravitational and rotational forces can theoretically twist space-time into loops, creating CTCs. But there's a catch. Most models predict that the center of a rotating black hole, known as a singularity, will be ring-shaped rather than point-shaped. This ring feature could potentially serve as a gateway to the CTC. However, powerful gravitational forces could also create a barrier, known as the Cauchy horizon, beyond which the laws of physics are violated. The study of CTCs and black holes is fraught with paradoxes and uncertainties. For example, if CTCs exist, they can lead to paradoxes in which cause and effect are reversed. This has prompted some physicists to propose the chronology defense hypothesis, which suggests that the laws of physics prevent such paradoxes. Imagine the possibilities and dangers of approaching a rotating black hole. Would we ever be able to navigate safely through such a treacherous region of space-time? And if we could, what would we find on the other side? Another universe? Another time? In addition to black holes and closed time-like curves, there's another cosmic mystery that could potentially open a path through time: cosmic strings. These hypothetical one-dimensional cracks in the universe may be remnants of the Big Bang itself. Cosmic strings are thought to have formed in the early moments of the universe as they cooled down after the hot and dense state of the Big Bang. These strings would have been thinner than an atom, but incredibly dense, and would have had a tremendous gravitational pull. Although still theoretical, cosmic strings offer intriguing possibilities for time travel. Physicists J. Richard Gott and William Hiscock have made significant contributions to our understanding of these mysterious objects. Gott suggested that a cosmic string traveling at the speed of light could theoretically distort space-time enough to create a loop allowing time travel into the past or future. However, the existence of cosmic strings is still a matter of debate. Their detection would require astronomical observations on scales that are currently beyond our capabilities. Moreover, if they do exist, harnessing their power for time travel would be a challenge. Now, let us return to quantum entanglement. We've already explored how entangled particles are connected in ways that transcend ordinary spatial distances. Can they be bound in time? Some theories suggest that entangled particles can be used to transmit information not only in space, but also in time. Imagine a future in which quantum entanglement is used to create a kind of quantum internet that allows instant communication across eras. The intersection of cosmic strings and quantum entanglement is a frontier of theoretical physics rife with unanswered questions and untapped potential. Researchers are exploring how the two phenomena might be connected and what this might mean for our understanding of time travel. Imagine a scenario in which cosmic strings are manipulated at the quantum level through entanglement. This would represent a merger of the very large and the very small, a meeting point of cosmic and quantum scales that could revolutionize our concept of time travel. As we venture into the realm of time travel, we face many paradoxes and riddles. These are not just intellectual exercises. They are fundamental questions that can make or break the possibility of time travel. First of all, this is the grandparent paradox. Imagine going back in time and not allowing your grandparents to meet. If they never meet, one of your parents will never be born, and therefore neither will you. But if you were never born, how would you even be able to travel through time? The grandfather paradox raises questions about causality and the nature of time itself. Some theorists suggest that such paradoxes can be resolved through the existence of parallel universes, where each solution generates a new timeline. Another confounding bootstrap paradox is named after the popular expression, pulling yourself up by your bootstraps. Imagine going back in time to give Shakespeare a copy of your works, which he then claims as his own. Where, in that case, did these works originate? The bootstrap paradox creates a closed loop of cause and effect with no apparent origin. It challenges our linear understanding of time and suggests that cause and effect may not be as simple as we think. Another paradox, the paradox of predestination, is when a time traveler's actions in the past lead to the very event he was trying to prevent. This raises questions about free will and determinism, and whether we can ever really change the course of history. The study of time travel paradoxes is not just a playground for philosophers. It's a serious area of research in physics and metaphysics. The resolution of these paradoxes may shed light on time travel. While we stand on the threshold of scientific discovery, the future of time travel remains a mystery shrouded in paradoxes, theories, and cosmic phenomena. What was once the realm of science fiction is gradually approaching the realm of real science. From cosmic strings to quantum entanglement, from spinning black holes to closed time-like curves, we explore the theories and possibilities that could one day make time travel a reality. Current research is paving the way for new experiments, new technologies, and perhaps even a new understanding of the structure of reality. But as we teeter on the edge of cosmic horizons, one question becomes more important than all others. Are we ready for what we might find? Time waits for no one, but what if we could wait for time? What if the closest star to our Sun is hiding a world where humans might one day live? In 2016, astronomers discovered Proxima Centauri b, a planet just 4 light-years away. But getting to this distant neighbor isn't just a dream. It's a challenge that modern science is beginning to address. Imagine a journey of more than 25 trillion miles. The technology we have today, such as the ion engines used in deep space missions, pales in comparison to what would be needed for such a journey. But hidden in the blueprints of a decade ago and cutting-edge research are the keys to interstellar travel. But distance isn't the only obstacle we have to overcome. Today, we'll talk about it and find out if humanity's next giant leap can take us to Alpha Centauri. The dream of interstellar travel has been part of the human imagination for centuries. But it wasn't until the 20th century that science began to catch up with science fiction. The journey begins with a momentous moment in 1961, when Yuri Gagarin became the first man to orbit the Earth. This achievement paved the way for space exploration, proving that humans could survive and work beyond our planet. Then came the Apollo program, including the historic 1969 lunar landing. Neil Armstrong and Buzz Aldrin's footsteps on the lunar surface were not only victory for humanity, but also a demonstration of our ability to reach and explore other celestial bodies. In the 1970s, Voyager missions provided invaluable data on the outer planets and heliosphere. These probes, now in interstellar space, carry with them golden records, messages intended for any intelligent extraterrestrial life that might encounter them. The voyages of Voyager 1 and Voyager 2 have given us a glimpse of the vastness of space and the inspiring potential of travel beyond our solar system. But humanity does not stand still. In recent years, the development of advanced propulsion systems has been crucial. Ion engines, used in missions such as NASA's Dawn spacecraft, enable long-duration missions with unprecedented efficiency. These engines use electrically charged particles to generate thrust, a method far more efficient than traditional chemical rockets. At the same time, our understanding of the universe has been revolutionized with the discovery of exoplanets, planets orbiting stars outside our solar system. The first confirmed exoplanet discovery occurred in 1992 when astronomers discovered 2 rocky planets orbiting a pulsar. This discovery shattered previous notions and opened the floodgates to the search for other worlds. In 1995, the discovery of 51 Pegasi b, the first exoplanet found orbiting a Sun-like star, further reinforced the idea that planets are fairly common in the universe. This gas giant, located about 50 light-years away, ushered in an era of exoplanet discoveries that continues to this day. Among the most exciting discoveries is Proxima Centauri B, discovered only in 2016. This exoplanet orbits Proxima Centauri, the closest star to our Sun, at a distance of only 4.24 light-years. Proxima Centauri B is in the habitable zone of its star, where all the conditions for liquid water to exist could exist. This proximity and potential habitability make this planet a prime target for future exploration and even potential colonization. The discovery of Proxima Centauri B was made possible thanks to the radial velocity method, which allows you to detect subtle fluctuations in the motion of the star caused by the gravitational pull of the orbiting planet. So far, this method has helped to identify more than 1,000 exoplanets, each of which has become the next step in the search for a world on which life may exist. The feasibility of interstellar travel depends directly on our ability to develop efficient and powerful propulsion systems. Current space travel technology has made significant advances, but it still falls short of what's needed to travel beyond our solar system. Ion engines represent one of the most advanced forms of space propulsion in use today. Unlike traditional chemical rockets, which use explosive reactions to create thrust, ion engines use electricity to ionize the propellant, usually xenon gas. The ionized gas is then accelerated using an electric field, creating sustained and highly efficient thrust. NASA's Dawn spacecraft, launched in 2007, is a prime example of the capabilities of ion propulsion. Dawn's mission was to explore the asteroid belt, in particular the protoplanet Vesta and the dwarf planet Ceres. Ion propulsion allowed Dawn to enter and exit orbits around these bodies, which would have been prohibitively expensive with conventional rockets. Ion engines have a high specific impulse, which means they use fuel much more efficiently than chemical rockets. This efficiency is critical for long-duration missions because it allows spacecraft to take less fuel with them. However, the trade-off is that ion engines produce much less thrust than chemical rockets. This makes them unsuitable for launching spacecraft from the Earth's surface, where enormous thrust is needed to overcome gravity. Another milestone in the development of modern propulsion technologies was NASA's New Horizons probe. Launched in 2006, the spacecraft was supposed to explore Pluto and its moons, providing mankind with the first images of this distant world from an incredibly close distance. The probe's journey did not stop at Pluto, but continued on to the Kuiper Belt, a region filled with icy bodies and remnants of the formation of the solar system. New Horizons used a combination of chemical propulsion and gravity assists to achieve its high speed. After launch, the spacecraft received gravitational assistance from Jupiter, which increased its speed and directed it toward Pluto. This maneuver allowed New Horizons to travel more than 3 billion miles in just 9 years. An amazing accomplishment considering such vast distances. While New Horizons demonstrates the height of current space travel capabilities, it also highlights its limitations. Despite speeds of more than 36,000 miles per hour, it took the spacecraft nearly a decade to reach Pluto, and even longer to continue its journey into the Kuiper Belt. For interstellar travel, where distances are measured in light years, we need propulsion systems capable of much higher speeds over long periods of time. Meanwhile, the most intriguing and historically significant advanced propulsion concepts is nuclear pulse propulsion. This technology, conceived during the Cold War era, involves using a series of controlled nuclear explosions to propel a spacecraft. The concept was first proposed by physicist Stanislaw Ulam in the 1950s and later developed into the Orion project. The basic principle of nuclear pulse propulsion is relatively simple. Small nuclear bombs are thrown behind the spacecraft and detonated, and the resulting explosions provide powerful thrust, A large pusher plate attached to the spacecraft absorbs the force of the explosion, propelling the spacecraft forward. The potential of the Orion project was enormous. Calculations showed that such a spacecraft could reach speeds of up to 10% of the speed of light, making it one of the fastest of the proposed propulsion methods. Such a capability would significantly reduce travel time to nearby star systems, including our neighbor, Alpha Centauri. Meanwhile, in recent years, the Breakthrough Starshot initiative has become one of the most ambitious attempts to achieve interstellar travel within our lifetime. The goal of this international science project is to send a probe to the same Alpha Centauri and possibly reach it in just 20 years. Breakthrough Starshot's main innovation is the use of a light sail propelled by an array of powerful ground-based lasers. This light sail, which is a thin and highly reflective sheet, will accelerate to extremely high speeds by transmitting momentum from millions of laser beams. Unlike traditional propulsion methods, this system carries no fuel, making it extremely lightweight and, in theory, capable of speeds up to 20% of the speed of light. Realizing this technology, however, is not without its challenges. The proposed laser array would require a total optical power of about 100 gigawatts, about 100 times the capacity of the world's largest battery. Synchronizing the roughly 100 million lasers to focus their beams on the light sail is a daunting technical hurdle. To solve this problem, researchers from the Australian National University have proposed using a laser guide satellite to help maintain an accurate target throughout the voyage. Despite such challenges, the potential benefits of this technology are enormous. If successful, the Breakthrough Starshot mission will be able to transmit detailed scientific data and images from Alpha Centauri, providing unprecedented insight into our nearest neighboring star system. While light sails represent a promising near-future technology, other cutting-edge concepts are pushing the boundaries of our understanding of physics. Among them is the theoretical warp drive. Inspired by Einstein's general theory of relativity, a warp engine would manipulate space-time itself, compressing space in front of the spacecraft and expanding it behind, allowing the craft to travel faster than the speed of light without violating the laws of physics. The concept of warp drive gained attention after the 1994 publication of a paper by physicist Miguel Alcubierre, who proposed a theoretical basis for such a drive. Although the concept is currently speculative and requires exotic matter with negative energy density, warp drive remains a tantalizing possibility for future interstellar travel. Another innovative concept is the Freeman-Dyson interstellar jet engine. This hypothetical propulsion system would harness the energy of a star, using a series of mirrors or lenses to focus stellar energy onto a spacecraft. The collected energy would then be converted into thrust, propelling the spacecraft at high speeds. While Dyson's concept is intriguing, its practical realization faces serious obstacles. Capturing and converting enough stellar energy to achieve meaningful thrust would require materials and engineering capabilities many times greater than our current technology. Perhaps the most powerful of the proposed propulsion systems is a propulsion system based on antimatter. Antimatter, coming into contact with matter, annihilates both particles, releasing huge amounts of energy. A spaceship powered by antimatter can theoretically reach speeds approaching a significant fraction of the speed of light. The potential of antimatter propulsion is staggering, but so are the challenges. Antimatter production is currently a highly inefficient and expensive process, and its safe storage represents additional challenges due to its highly reactive nature. Despite these obstacles, antimatter research continues as it promises to be an unprecedentedly efficient engine. Huge distances present the most obvious obstacle. Nevertheless, even with a modestly efficient propulsion system, only a fraction of the difficulties would be overcome. Interstellar travel is an enormous undertaking fraught with technical and logistical challenges. Even with the most advanced propulsion systems, traveling to our nearest star system, Alpha Centauri, requires overcoming enormous technical obstacles. One of the main technical problems is protection against radiation. Space is filled with high-energy particles from the Sun and distant space sources. Prolonged exposure to this radiation can be deadly to both humans and sensitive electronic equipment. Modern spacecraft use a combination of physical and electronic shielding to protect against radiation, but these methods are insufficient for the prolonged exposure expected during interstellar travel. Advanced materials and innovative shielding techniques are being explored. These include the use of magnetic fields to deflect charged particles and the development of new composite materials that provide better protection without excessive weight gain. However, creating effective and lightweight radiation shielding remains a major challenge. Another technical hurdle is maintaining the structural integrity of the spacecraft themselves over the long term. Spacecraft designed for interstellar travel must be able to withstand the stresses associated with launch, long stays in space, and possibly collisions with micrometeoroids and other space debris. The high speeds required for interstellar travel exacerbate these risks, since at such speeds even tiny particles can cause significant damage. Engineers are exploring advanced materials such as carbon composites and reinforced alloys to improve spacecraft durability. In addition, modular designs that allow for in-flight repair and maintenance could be critical for long-duration missions. The vast expanse of space presents another logistical challenge. Even at a significant fraction of the speed of light, it would take decades to reach the nearest star systems. Advances in autonomous systems and long-term life support are needed to keep a spacecraft operating reliably for such a long time. Solutions such as hibernation or suspended animation are already being explored, but these technologies are still in the experimental stage. In addition to technical and logistical challenges, interstellar travel faces serious economic and political obstacles. The cost of developing, building, and launching an interstellar mission is astronomical, no pun intended. Governments, private enterprises, and international consortia will have to collaborate and pool resources. Historically, space exploration has been funded primarily by national governments, but the growing involvement of private companies such as SpaceX and Blue Origin suggests a potential shift to more diverse funding models. The search for habitable planets, especially in the Alpha Centauri system, is one of the key areas of modern astronomy. As you may have already realized, the discovery of Proxima Centauri b in 2016 was an important milestone that showed the possibility of habitable worlds in our nearest neighboring star system. This exoplanet has sparked numerous missions and research initiatives aimed at figuring out its characteristics and potential to support life. To continue this research, the European Southern Observatory has developed a new instrument designed specifically to search for exoplanets in the Alpha Centauri system. This advanced instrument, part of the Very Large Telescope in Chile, enhances our ability to detect Earth-like planets by improving the accuracy of radial velocity measurements. The instrument aims to identify Earth-sized planets by detecting the tiny gravitational fluctuations they cause in their host stars. Focusing on Alpha Centauri A and B, the two Sun-like stars in the system, this instrument seeks to detect additional planets that may lie within their habitable zones. The improved sensitivity and resolution of this technology promises to reveal planets that have not previously been detected, giving a clearer picture of the potential for habitable worlds in our nearest star system. The importance of discovering a habitable planet in the Alpha Centauri system cannot be overemphasized. Such a discovery would be a tremendous step forward in our quest to understand how widespread habitable conditions are beyond our solar system. A habitable planet in such close proximity would be a prime candidate for future interstellar missions and a potential target for human colonization. Recent discoveries in the search for habitable exoplanets have been promising. For example, late this spring, astronomers discovered the Earth-like exoplanet Gliese 12b, located just 40 light-years away. This planet, comparable in size to Venus, orbits a red dwarf star and is estimated by scientists to have a surface temperature of about 107 degrees Fahrenheit. The discovery of such a planet, which may have an atmosphere, provides insight into the conditions necessary for a planet to retain an atmosphere and for liquid water to exist. The discovery was made possible by NASA's Transiting Exoplanet Survey satellite, which detects exoplanets by observing a small, dimmer star as the planet passes in front of it. During such transits, the star's light passes through the exoplanet's atmosphere, allowing astronomers to analyze its composition using transmission spectroscopy. The significance of Gliese 12b goes beyond its potential habitability. It serves as a valuable point of comparison for understanding why Earth and Venus, despite their similarities, have very different environments. By studying Gliese 12b, scientists hope to learn more about the atmospheric retention and evolutionary pathways of Earth-like planets orbiting cold stars, which are the most common type of stars in the Milky Way. Gliese 12b's estimated size may be as large as Earth or slightly smaller, comparable to Venus in our solar system. Current efforts to find and study potentially habitable planets around Alpha Centauri and other nearby stars continue to evolve. Instruments such as JWST are expected to play a crucial role in this search, providing a deeper understanding of the conditions that could make these planets habitable. On the other hand, no one is saying that humans should be the first to explore these distant worlds. Even without the advanced technology necessary for human survival, we can still send probes to pave the way. Intelligent robotic probes and artificial intelligence have a key role to play in the future exploration of interstellar space. These technologies can operate autonomously, handling complex tasks without direct human intervention, making them ideal for long-duration missions far beyond our solar system. One of the most intriguing concepts in this regard is the so-called von Neumann probes. These theoretical, self-replicating machines could explore the galaxy using local materials to create their replicas, exponentially increasing the number of probes with each replication. This approach could provide extensive exploration and potential colonization without requiring constant resupply from Earth. However, when it comes down to human space exploration, the idea of interstellar arcs and self-sustaining habitats represents a visionary approach to colonizing distant star systems. These massive spacecraft would host large communities, providing everything needed to sustain life during multi-generational journeys to other stars. These habitats will be equipped with advanced life support systems, agricultural facilities, and social infrastructure to ensure the well-being of their inhabitants. In conclusion, while our current technology limits us to relatively modest space travel, these advanced concepts offer a glimpse into a future in which we can transcend the space barriers that confine us to our solar system. As technology advances, these concepts may well move from science fiction to reality, paving humanity's path to the stars. The moon has always been a beacon of mystery and wonder, but beyond its radiant beauty and folkloric tales, the moon holds secrets that have eluded us for centuries. Among these mysterious features is the moon's south pole, a region shrouded in perpetual shadow and intense cold, untouched and unexplored by any previous lunar mission. This is the story of Chandrayaan 3, India's daring journey into uncharted territory. Launched on a journey of more than 238,600 miles, Chandrayaan-3 embarked on a mission not just of distance, but of discovery. Its purpose? To unravel the mysteries of the Moon's south pole, a place where sunlight barely reaches, an area where the terrain is so treacherous that you have to wade through an endless maze of craters and rocks. Here, in this alien landscape, Chandrayaan-3 sought answers to questions that have puzzled scientists for decades. What lies beneath the surface of this mysterious region? Do earthquake-like tremors shake this silent world? And the most exciting question is whether water, the elixir of life, exists here in the form of ice. When Chandrayaan-3 ventured beyond Earth, it carried with it the aspirations of a nation and the curiosity of the world. Its primary goal was clear, yet challenging: to achieve a soft landing near the Moon's south pole, a feat that had never before been accomplished. From the busy Mission Control Center of the Indian Space Research Organization, a team of dedicated scientists and engineers piloted this ambitious mission. Their expertise helped Chandrayaan-3 traverse the space void, overcoming the challenges of lunar orbit insertion and descent. The south pole of the Moon is a landscape unlike any other. Here, the terrain is a patchwork of craters and mountains, many of which are shrouded in perpetual darkness. The challenge was not just to land, but to land safely in an area where the terrain is unforgiving and most slopes are quite steep. When the Vikram landing module separated from the orbiter, it began its descent. The landing module, equipped with advanced sensors and engines, began its perilous journey to the surface of the Moon. Imagine a spaceship autonomously navigating a maze of craters and boulders in search of a patch of land safe enough to land on. The landing module's onboard systems were hard at work, analyzing every inch of the terrain below. Against this treacherous landscape, the landing module also struggled with extreme temperatures. The Moon's south pole is a place of stark contrasts. The sun barely rises above the horizon, while shadows hide frigid temperatures that can drop to minus 382 degrees Fahrenheit. As the landing module made its final approach, the hearts in the Flight Control Center beat harder. Every second was decisive, every maneuver a test of human ingenuity and technological prowess. With a light thud, Vikram landed, marking an historic moment not only for India, but for lunar exploration in general. In the silence of the Moon's south pole, Chandrayaan-3 began its mission of exploration and discovery. So, after the historic landing of Chandrayaan-3, a new chapter in lunar exploration began. The mission's goal was to maximize the study of the Moon's characteristics, especially its elusive exosphere and ionosphere, and to establish the range of temperature variations just beneath its surface. The lunar exosphere, the thin layer of gases surrounding the Moon, holds the key to the satellite's past and present. Unlike Earth's robust atmosphere, the Moon's exosphere is so rarefied that it almost resembles a vacuum. The Chandrayaan-3 instruments, developed using the latest technology, are designed to measure the density and composition of this elusive layer. In addition to the exosphere, the mission delved deeper into the Moon's ionosphere. This layer, formed by solar energy ionizing atoms in the exosphere, plays a crucial role concerning lunar communication and navigation. The Chandrayaan-3 measurements were designed to provide unprecedented information on the density and behavior of the ionosphere, which is important for future lunar missions and potential human habitats. Another intriguing aspect of the mission was studying the temperature variations just beneath the lunar surface using one of 4 instruments on the landing module, CHASTE, or Chandra's Surface Thermophysical Experiment. The temperature probe, immersed in the lunar regolith, was tasked with the critical mission of mapping the thermal profile of the lunar soil. The results of Chandrayaan-3 revealed a sharp contrast in temperatures. On the surface, during a lunar day, temperatures rose dramatically to 140 degrees Fahrenheit. While just 8 centimeters deeper, they dropped significantly to 14 degrees Fahrenheit, demonstrating the lunar soil as a potential thermal insulator. This discovery provided new opportunities for future lunar habitats. suggesting that the lunar regolith could serve as a thermal insulator, protecting astronauts from the moon's harsh extreme temperatures and harmful radiation. These studies were more than just scientific endeavors. They were stepping stones toward a future in which the moon could be a gateway to future space exploration. Mission results on the lunar exosphere, ionosphere, and subsurface temperature laid the foundation for understanding the moon's environment and its potential to support human life. Standing in the vast lunar landscape, Chandrayaan-3 was ready to detect a phenomenon that had not been observed for more than 50 years, a lunar earthquake. The mission succeeded in shedding light on one of the most intriguing and least understood aspects of the moon. The Instrument for Lunar Seismic Activity, or ILSA, a seismic instrument, was designed to detect the slightest tremors on the moon, and it did. Chandrayaan-3 detected what looked like a lunar earthquake, a significant discovery given that the last such observation was made during the Apollo missions in the early 1970s. Lunar quakes are fundamentally different from earthquakes. While Earth's seismic activity is largely due to the movement of tectonic plates, the Moon, which is devoid of these plates, experiences earthquakes for a variety of reasons. These tremors can last much longer than earthquakes, sometimes up to an hour, and their origin is a subject of scientific interest. The Chandrayaan-3 data suggests several possible causes for these earthquakes. One theory is a collision with meteoroids, which could cause shock waves that penetrate the moon's crust. Another is Earth's gravitational pull, causing tidal forces that load the lunar crust. And finally, extreme temperature fluctuations on the moon's surface can cause expansion and contraction, leading to earthquakes. These earthquakes are not just surface phenomena, they're windows into the moon's interior. By analyzing the seismic waves, scientists can infer the composition and structure of our satellite's interior, which resembles a sonogram of the lunar interior. Such information is of great importance for understanding the formation and evolution of the moon. The detection of a lunar earthquake by the Chandrayaan-3 spacecraft has not only provided a glimpse into the dynamic nature of our celestial neighbor, but has also opened up new insights into the geological processes that shape the moon. To unravel the geologic mysteries of the moon, Chandrayaan-3 carried out another exploration. Among the most intriguing finds was the discovery of sulfur, an element whose presence on the moon has been shrouded in mystery. The Laser-Induced Breakdown Spectroscope, or LIBS rover, a marvel of scientific instrumentation, vaporizes tiny samples of lunar soil using high-energy laser pulses. When the plasma emits light, the spectroscope analyzes its wavelength, thereby revealing the presence of various elements, including sulfur. Sulfur on the moon is a significant find. On Earth, sulfur is often associated with volcanic activity, raising questions about similar processes on the moon in the past. Its presence could provide insight into the volcanic history of the moon and the processes that shaped its surface. In addition to sulfur, another key objective of Chandrayaan-3 was the search for water ice, a search that's intrigued scientists for decades. Water ice on the moon is not just a scientific curiosity, it's a potential resource for future human missions, offering water for life support and fuel production. Despite high hopes, Chandrayaan-3, like its predecessors, found no direct evidence of water ice on the moon's surface. However, the lack of direct evidence is not a conclusion, but a clue leading to new hypotheses. One theory is cold trapping, in which water vapor can migrate to permanently shadowed craters at the poles, freezing into ice. The detection of sulfur adds another layer to this theory, as sulfur may be trapped with the water ice and released as a result of the breakdown of water molecules by high-energy solar radiation. The lack of direct evidence for the existence of water ice raises important questions. Is the ice deeper beneath the surface, shielded from detection by the insulating properties of the lunar soil? Or is its prevalence more heterogeneous and elusive than previously thought? During its exploration of the moon's south pole, Chandrayaan-3 found more than just sulfur. The rover's LIBS instrument made the first ever in situ measurements of the elemental composition of the lunar surface in this region. In addition to sulfur, the instrument detected aluminum, calcium, iron, chromium, and titanium, each element reflecting part of the complex geologic history of the lunar surface. Further measurements added new details to this discovery, further revealing the presence of manganese, silicon, and oxygen. These elements, each with its own unique spectral signature, provided clues to the formation of the Moon and its evolutionary history. Studies of the presence of hydrogen, a key component in the search for water, also continue. The mission's discovery of these elements and the ongoing search for water ice underscore the dynamic and complex nature of the Moon's geology. Each discovery, each unanswered question, moves us further in our quest to understand our nearest celestial neighbor and prepares us for the next steps in lunar exploration. As the Chandrayaan-3 mission at the Moon's South Pole opened a new chapter in lunar exploration, it also paved the way for the next ambitious leap, the Lunar Polar Exploration Mission, LUPEX for short. This joint venture between the Indian Space Research Organization and Japan Aerospace Exploration Agency is scheduled to launch no earlier than 2026. LUPEX plans to send an unmanned lunar lander and rover to further explore the South Pole region of the Moon. JAXA will likely provide the H-3 launch vehicle and rover under development, and ISRO will provide the lander. This mission represents a significant step in international cooperation on lunar exploration. The mission's goals are multifaceted. It will demonstrate new surface exploration technologies critical for sustained lunar exploration in the polar regions. Precise landings will be achieved by using a feature-matching algorithm and navigation equipment derived from the JAXA Smart Lander for Investigating Moon mission. The LUPEX rover will carry several instruments from JAXA and ISRO, including a drill capable of collecting samples from a depth of 5 feet, 1.5 meters. Finding and analyzing water are key goals of the mission, and the potential discovery of water ice could be a game-changer for future lunar missions. In parallel with LUPEX, ISRO's Chandrayaan-4 mission, designed to return samples from the Moon, is in the planning stage. Scheduled for launch by 2028, Chandrayaan-4 will consist of 4 modules: a transition module, a descent module, an ascent module, and a re-entry module. The ambitious goal of the planned mission is to return soil samples from the Moon, which will provide invaluable information about the lunar environment. The mission will involve complex maneuvers, including sample collection, docking in lunar orbit, and returning samples to Earth. Chandrayaan-3's innovative discoveries, from the detection of sulfur and other elements to the study of lunar earthquakes, have revealed new layers of the Moon's mysterious nature. These results provide crucial insight into the Moon's geology, its internal structure, and the potential for future lunar habitats. Looking ahead, the future of lunar exploration is promising. Missions like LUPEX and Chandrayaan-4, building on the legacy of the previous ones, will continue to explore the mysteries of the Moon. India's role in these endeavors is not only that of a participant, but also that of a pioneer. Such events truly inspire us to look beyond the boundless mysteries of the cosmos. The deeper we look into the universe, the more mysteries it reveals to us. Gravity, the invisible force that binds the cosmos together, may not be as unchanging as we once thought. From ancient civilizations to Einstein's groundbreaking discoveries, our understanding of gravity has constantly evolved. However, recent discoveries suggest that there may be a cosmic glitch on the grandest of scales. A subtle deviation in the force governing galaxies and stars. Ancient scientists pondered the nature of gravity, laying the foundation for Newton's elegant laws. But it was Einstein in the early 20th century who changed our perception. His theory of general relativity describes gravity not as a force, but as a curvature of space-time itself. Despite its success in predicting phenomena such as black holes and gravitational waves, Einstein's theory has its limitations. When we turn our eyes to the scale of galaxy clusters and beyond, we encounter inconsistencies. Gravity seems to weaken slightly over billions of light years, and it's this phenomena that researchers now call a cosmic glitch. This anomaly may hint at new physics, perhaps an extension of the standard cosmological model to include a varying gravitational constant. Such a modification could reconcile these inconsistencies without reversing the established successes of general relativity. The discovery of a cosmic glitch is forcing us to rethink our understanding of gravity. Could this be the first clue in a new puzzle that will eventually lead us to a theory that unifies the fundamental forces of nature? Long before the scientific revolution, ancient civilizations had encountered the concept of gravity, although they understood it in very different ways. The Greeks, for example, believed in the geocentric model, in which the Earth was the center of the universe. Aristotle argued that objects fall in the direction of their natural place, and this theory dominated Western thought for centuries. In ancient India, Hindu scriptures describe the concept of gravity as an inherent force that pulls objects toward the Earth. Similarly, the Chinese philosopher Mozi in the 4th century BC suggested that objects fall because of the force of the Earth's energy. These early ideas, although primitive by modern standards, laid the foundation for future scientific research. It was not until the Renaissance that a more precise understanding emerged. The work of Copernicus, Galileo, and Kepler challenged Aristotelian views, paving the way for the pioneering work of Isaac Newton. Newton's formulation of the law of universal gravitation in the 17th century was a monumental leap. He described gravity as the force that attracts two bodies to each other proportional to their masses and inversely proportional to the square of the distance between them. This elegant equation united the heavens and the earth under a single universal law. In the early 20th century, Albert Einstein revolutionized our understanding of gravity. He proposed the general theory of relativity, which described gravity not as a force, but as a curvature of space-time caused by mass and energy. Einstein's equations suggested that massive objects such as stars and planets warp the fabric of spacetime, creating what we perceive as gravity. This concept was visually confirmed during the 1919 solar eclipse expedition led by Sir Arthur Eddington. By observing the bending of starlight around the sun, Eddington provided one of the first experimental confirmations of the general theory of relativity. Consider this: almost a century ago, Einstein added fudge factor to his equations to bring them in line with the then accepted idea of a static universe, and later called this factor his greatest mistake. However, this very constant, lambda, reappeared many years later to explain the accelerating expansion of the universe. Einstein's theory also predicted phenomena such as black holes and gravitational waves that we have only begun to observe in recent years, further confirming the validity of his theory. The Event Horizon Telescope's image of a black hole in 2019 and LIGO's detection of gravitational waves in 2015 were monumental achievements in modern astrophysics. Despite its successes, however, general relativity has its limitations. It's inconsistent with quantum mechanics, the basis for understanding the subatomic world. This has led scientists to search for a more comprehensive theory that unites these two pillars of physics. In the quest to understand the universe, scientists have discovered anomalies that challenge our generally accepted understanding of gravity. These inconsistencies indicate that our current theories, while robust, may be incomplete. The general theory of relativity proposed by Albert Einstein has become a cornerstone of modern physics. The theory has been remarkably successful in explaining a wide range of phenomena, from the orbits of planets to the behavior of light around massive objects. However, recent research points to potential inconsistencies when the general theory of relativity is applied at cosmic scales. Recent research conducted by Robin Y. Wen and colleagues in 2024 hypothesized a cosmic glitch in gravity. Their research suggests that the gravitational constant may not be exactly constant over vast cosmic distances. In particular, gravity appears to be about 1% weaker when it comes to distances of billions of light years. This anomaly causes difficulties in our understanding of what's happening because it implies a deviation from Einstein's theory of extreme scales. To solve this problem, scientists propose a modification of the standard cosmological model, known as lambda, cold dark matter. This adaptation involves adding a new parameter that slightly corrects the gravitational constant on cosmic scales, without affecting its proven accuracy on smaller scales. The conflict between general relativity and quantum mechanics further complicates our understanding of gravity. General relativity best describes large-scale structures, such as galaxies and black holes, while quantum mechanics provides the best framework for understanding particles on the smallest scales. However, the two theories are fundamentally incompatible. One of the most striking proofs of this contradiction is the behavior of black holes. The general theory of relativity predicts the existence of singularities, points of infinite density at the centers of black holes. In contrast, quantum mechanics suggests that such infinities cannot exist, indicating the need for a new theory that could unify the two systems. Recent advances in technology, such as precise measurements of the cosmic microwave background by the Planck satellite, have provided new data that both confirm and refute existing theories. These observations have led to the discovery of the Hubble tension, a significant discrepancy between the observed and predicted expansion rate of the universe. The Hubble contradiction suggests that either our understanding of the early universe or the nature of dark matter and gravity needs revision. The cosmic glitch theory, which introduces a small change in the gravitational constant, offers one potential solution to this problem. In addition, the detection of gravitational waves by the LIGO and Virgo collaborations has opened new possibilities for testing gravitational theories. These observations provide an opportunity to observe the universe in a new way, potentially revealing deviations from the general theory of relativity that could not be detected before. The intersection of these anomalies with the predictions of quantum mechanics could lead to revolutionary discoveries. Experiments conducted at CERN at the Large Hadron Collider are aimed at exploring the boundaries between these two realms, searching for evidence that could bridge the gap between general relativity and quantum mechanics. In search of understanding of gravitation, some scientists suggest that it may not be a fundamental force, but rather an emergent phenomenon arising from deeper principles. This idea does not the traditional ideas about gravitation, but rather opens new ways of theoretical research. One well-known alternative is modified Newtonian dynamics, or MOND. Proposed by Mordecai Milgrom in the early 1980s, the theory suggests that Newton's laws need adjustment at the very low accelerations, characteristic of the outskirts of galaxies. According to MOND, these changes can explain the observed rotation curves of galaxies without involving dark matter. MOND has had some success in predicting the behavior of stars and galaxies, where traditional theories of gravity fail. However, it is unable to explain phenomena on large cosmic scales, such as galaxy clusters and the cosmic microwave background, where dark matter remains a more acceptable explanation. Another interesting theory is emergent gravity, Eric Verlin proposed in 2010. Verlin suggests that gravity is not a fundamental interaction, but arises from thermodynamic principles of information storage on holographic screens. From this point of view, the universe can be described as a hologram. where gravity arises from changes in entropy associated with the information stored on these screens. To simplify, imagine the universe as a giant laboratory where books, information, are stored on shelves, holographic screens. The arrangement and number of books change over time, affecting the overall structure and creating what we think of as gravity. Berlin's emergent gravity has intriguing implications for our understanding of dark matter. Instead of invisible particles, the effects attributed to dark matter may be a consequence of emergent properties of space-time itself. This theory allows us to take a new look at the connection between gravitation and thermodynamics. In addition to Mond and Berlin's theory, there are several other alternative approaches. One such theory is modified gravity, or simply MOG, proposed by John Moffat, which introduces additional gravitational fields to explain the rotation curves of galaxies and the dynamics of galaxy clusters without dark matter. MOG suggests that these additional fields modify the strength of gravity on different scales. In addition, the concept of entropic gravity, closely related to Berlin's ideas, suggests that gravity arises from the tendencies of systems to increase entropy. This thermodynamic interpretation is consistent with the principles of statistical mechanics, providing a new lens through which gravitational interactions can be viewed. These alternative theories, although not universally recognized, open before us new perspectives and require further research and experiments. They force us to reconsider the view of gravitation not as an inherent force of nature, but as a consequence of deeper, fundamental principles. As we move toward the middle of the 21st century, our quest to understand gravity continues to push the boundaries of technology and knowledge. State-of-the-art experiments and missions are being designed to test the limits of our gravitational theories, yielding new insights and potentially revolutionary discoveries. One of the most significant ongoing projects is, of course, the acclaimed James Webb Space Telescope. JWST observations to date have been crucial for testing theories of gravity on the largest scales, especially those that predict deviations from general relativity. Another key player in gravitational research is the Large Hadron Collider at CERN. This particle gas pedal, the largest and most powerful in the world, collides protons at unprecedented energies. These collisions allow physicists to study fundamental particles and forces, including the potential discovery of particles that can mediate gravitational interaction at quantum scales. Experiments at the LHC are critical to understanding how gravity can combine with other fundamental forces. Space missions such as the Laser Interferometer Space Antenna, LISA, also loom on the horizon. Planned for launch in the mid-2030s, LISA will consist of 3 spacecraft forming a giant triangular interferometer in space. This facility will detect gravitational waves with much greater sensitivity than existing ground-based detectors, such as LIGO and Virgo. The goal of LISA is to observe gravitational waves from the merger of supermassive black holes, which will test Einstein's general theory of relativity and provide new insights into dark matter and dark energy. But let's get closer to home, where Event Horizon Telescope continues to make groundbreaking contributions. In 2019, EHT obtained the first ever image of the black hole M87, demonstrating the power of synchronizing telescopes around the world to create a planet-sized interferometer. EHT is now focused on even more precise observations of black holes, including the one at the center of our galaxy, Sagittarius A. These observations will test the predictions of the general theory of relativity in extreme gravitational fields. In addition, let us recall the already mentioned recent study by Wen et al., which proposes a cosmic glitch in gravity. suggesting that the gravitational constant may vary over cosmic distances. This study will be further tested with data from the Planck satellite and future cosmic microwave background experiments. Upcoming missions such as the Simons Observatory and CMB-S4 aim to make more precise measurements of the CMB that can confirm or refute the existence of such a glitch, offering a deeper understanding of the nature of gravity at the largest scales. In addition, the Vera C. Rubin Observatory, which will soon become fully operational, will conduct the Legacy Survey of Space and Time. This survey will map billions of galaxies, providing a detailed view of the structure and evolution of the universe. The data from LLST will help test theories of dark matter, dark energy, and gravity, and possibly reveal new phenomena that will change our current understanding. Another exciting frontier is the search for quantum gravity using benchtop experiments. These experiments use highly sensitive equipment to detect tiny gravitational effects on very small scales, where quantum mechanical effects become significant. Such experiments are designed to bridge between general relativity and quantum mechanics, which may lead to a unified theory of gravitation. These state-of-the-art experiments and missions represent the cutting edge of gravitational research. They are designed not only to test existing theories, but also to discover new phenomena that could revolutionize our understanding of the universe. Revising our understanding of gravity could have profound implications for cosmology, astrophysics, and technology. The anomalies and alternative theories that we've studied suggest that our understanding of gravity is far from complete. As our models improve, we can expect significant progress in several key areas. In cosmology, a more accurate model of gravity could solve existing mysteries, such as the nature of dark matter and dark energy. If gravity behaves differently over vast cosmic distances, it could provide a new explanation for the accelerated expansion of the universe and the distribution of galaxies. This could lead to a unified model of the cosmos that better integrates general relativity and quantum mechanics. For astrophysics, improved gravitational theories can improve our understanding of black holes, neutron stars, and other extreme environments. By accurately describing the behavior of matter under the influence of intense gravitational fields, we can better understand the life cycle of stars and the dynamics of galaxies. This knowledge may even reveal new types of astrophysical objects or phenomena. Technologically, advances in the understanding of gravity will undoubtedly spur innovations in various fields. For example, accurate measurements of gravitational waves can improve navigation systems and geophysical research. In addition, breakthroughs in quantum gravity could lead to new technologies based on quantum information and communication, revolutionizing computing and data transmission. Imagine a future in which our understanding of gravity will enable ultra-precise space-time sensors, leading to the development of autonomous vehicles, precision agriculture, and disaster prediction systems. As we wait for the launch of new missions, projects, and discoveries, the anticipation grows. Each step forward brings us closer to unlocking the mysteries of the universe, promising a future in which our understanding of gravity and the cosmos is richer and deeper than ever before.